Yeah. Good evening to all. I hope so. All of you might be joined. I'm just waiting. Okay. Yeah. Good evening. Good evening to all. Yesterday we have discussed about the alternator, three-phase alternator. Alternators there will be based on the phases. So far existing is single-phase alternators are there, two-phase alternators, and three-phase alternators also, right? But most of the power generation is by three-phase alternator. That I'm going to explain why. What is the advantages of the three-phase alternators? Yesterday we have seen when armature conductors can be kept on the stator, and 4 cases we have seen. The generated EMF or direction of induced EMF can be found. If conductor is, the case one is conductor is rotating, no assumption is required. When conductor is stationary, we need to assume opposite direction. When both conductor and poles rotating in same direction, if conductor is slower, we need to assume opposite direction. Conductor is faster, no assumption is required. And when both are rotating in opposite direction, whether conductor may be slower or faster, no assumption is required. We can consider in the same direction. Okay. So based on that, we have seen some objective questions, but whatever I have given the statements, they are the general statements and valid for everywhere, wherever you want, you can apply that. Okay, rotating machines, that will be valid. Fine. Yeah. Now, in this class, let us see the another important topic is phase sequence. I am sharing this board. Yeah. Okay. The another important topic today, what we are going to see is starting with the phase sequence. Phase sequence. Phase sequence, that is also called or phase order. Phase sequence is also called phase order. Now, let us see this. Phase sequence, phase order. Phase sequence is one of the important property of AC electrical energy, like frequency, phase sequence. Phase sequence is also one of the important property. We should have the complete idea about the phase sequence, and you should know how to change the phase sequence, right? So for example, two alternators are connected in parallel. What are the conditions for parallel operation? Their phase sequence must be same, and you should know what is the phase sequence of your alternator or another alternator. Or when if you want to connect the alternator to the grid already existing system, infinite bus bar, phase sequence must be same. So your phase sequence is same with the bus bar phase sequence, right? And you should know how to verify the phase sequence. You should know how to change the phase sequence. You should know your phase sequence is not correct, say, and you should know how to change the phase sequence, right? Very important property. And based on this also, so many questions that we are going to see after the end of this topic. And for synchronous motors, AC motors, if you change the phase sequence, what is going to happen? Direction of rotation will change. For alternator, you want to change phase sequence, what to do? First of all, what is the phase sequence? See, phase sequence, the definition of phase sequence is the order. Phase sequence is the order at which the maximum values of induced EMFs, or currents currents are obtained. Currents are obtained. Phase sequence is the order at which the maximum values of induced EMFs or currents are obtained. Are you getting? The order at which maximum value. In which phase first maximum value? Next in which phase? Next in which phase? First R phase, next Y phase, next B phase. That is a sequence. Okay. And before starting this phase sequence, as I told, there will be so many questions. First, let me start with the phase sequence, question on the phase sequence that we are going to realize. Yeah. See, phase sequence of three-phase alternator. Phase sequence of question is like this. Phase sequence of three-phase alternator. Phase sequence of three-phase alternator can be reversed. Can be reversed by changing the phase sequence of three-phase alternator can be reversed a bit by changing the direction of field rotation, B bit. By changing the direction of field current, C bit. Either A or B, D bit. Phase sequence cannot be reversed. Phase sequence cannot be reversed. Phase sequence cannot be reversed. This is your previous GATE examination question. Sorry. Okay, phase sequence of three-phase alternator can be reversed A bit by changing the direction of field rotation, B bit by changing the direction of field current, either A or B. Phase sequence cannot be reversed. Yeah. So what is the answers you are expecting? Tell me some of you. Okay. What's your answer? You are expecting either A or B. Some people are C, A, B. All options are okay. Yeah. Let us see. In this, by changing the A bit, by changing the direction of field rotation, that is possible. We can change the field rotation. You have taken this question now? Yes. Now listen. We can change the field rotation, but whether phase sequence changes or not, that we have to verify. By changing the direction of field current also we can change. That is in our hand. By changing the DC polarities, field current direction can be reversed. But phase sequence changes or not, that we have to verify. And both can be verified. Both can be reversed. Because alternator is a doubly faded machine, not doubly faded. Two inputs we are giving. What is that? One is mechanical power input, another one is DC electrical power input, DC excitation. So two inputs, doubly faded. The two feedings we are giving, mechanical power input and DC electrical power input for excitation. So both are possible. Both I can change. I can change the field rotation. I can change the field current. But whether phase sequence is depends on the field rotation or field current or both. Let us verify this. During this, I am going to take all possibilities. I will change all. I will verify for A option. I will verify B option. And finally, I will come to the conclusions. And thereby, we are going to see some other questions. Okay? Yeah. So, first of all, again, once I want to highlight what is that phase sequence. You should know the definition of phase sequence. Phase sequence is the order at which the maximum values of induced EMFs or currents are obtained. Order of maximum values. Order of maximum values. Okay. Yeah. Let me change all possibilities. In the options he has given, by changing the field rotation, field current, let us verify all. Let us verify all the things. See. Is a rotor. Yeah. Okay. On this, for the rotor, we are giving DC current. This is the direction of field current, IF, field current, because these are the polarities, plus and minus, plus and minus. This is R phase, say Y phase and B phase, R, Y, B, R phase, Y phase, B phase, three phase alternator, three phase alternator. And I can rotate both in clockwise and also counterclockwise direction. By using the prime mover, we can rotate in both directions. Similarly, let us check for another possibility also. I will change the field current. Just a minute. Yeah. R phase, Y phase, B phase. You also take down this diagram, but minus and plus, polarities are minus and plus, R phase, Y phase, B phase. Are you getting the difference between these two? Yes, field current direction has reversed. Field current direction has reversed. Take it fastly, and very important discussion we are going to see. Let us utilize our time effectively. Yeah. In two diagrams, I have reversed the field current because options are given. Is it depends on the field current or field rotation? I will change the rotation also, field rotation. Field current is reversed already. Yeah. See. For this first diagram, diagram 1, for this given field current direction, this act as a north pole, this act as a south pole. Correct? North pole and south pole. But second one, second diagram, field current is reversed. North pole becomes south pole becomes north pole. Okay. Yeah, I hope you can apply the thumb rule. Thumb rule. Thumb rule, fingers enter, curled fingers. Thumb give the flux. So when thumb is giving the flux means act as a north pole. North pole. Right? Okay. Yeah, I hope you have taken. Listen. For this given field current north pole, this is south pole. And when I am rotating this rotor, I am rotating this rotor in clockwise direction. Prime mover rotation. When prime mover is rotated in clockwise, this rotor will rotate in clockwise direction. Rotor rotate in clockwise direction. And when rotor is rotating, poles rotating. When poles rotate, flux also rotate. Rotating field is nothing but what? Rotating poles. Rotating field, rotating poles. So rotor is rotating. When rotor is rotating, right? Field is rotating. Now, then coming to what is the phase sequence? Phase sequence is the order at which the maximum values of induced EMF obtained. Maximum value. Now tell me here, at this instant, in which phase induced EMF is maximum? Tell me. Right now, in which phase induced EMF is maximum? R phase. R phase in this first diagram, because when conductor is under the pole, yesterday we have seen, when conductor is under the pole, EMF is maximum. So right now, north pole is under the R phase, induced EMF is maximum in the R phase. Induced EMF is maximum in the R phase at this instant. So therefore, this is, I am taking omega t, say, induced EMFs. R phase is first maximum. This is R phase, first maximum, ER. Of course, this is the instant actually where maximum values of instant I am taking. Of course, it is anyhow in the conductor, it will be sinusoidal. Yes, I am observing only peak values, maximum values, order of maximum value. So definitely, first maximum will be in the R phase. And after 120 degrees, what will happen? Rotor will rotate. When rotor is rotating, pole rotated. After 120 degrees, it will comes under the Y phase. It will comes under the Y phase. North pole is rotating. After 120 degrees, north pole will comes under the Y phase. Therefore, it is cutting the Y phase. North pole will cut the Y phase. So therefore, next maximum value will be in the Y phase. The Y phase. This is ER maximum, and this is EY maximum value. And another 120 degrees, I am taking only positive half cycles, enough. Positive half cycles, positive maximum value I am observing. Okay. So north pole is here. Right now, north pole is here. And after another 120 degrees, north pole will come to here. I am observing only with respect to north pole, dear students. Forget about south pole. Positive peak values I am taking. So when north pole is here, it is cutting first R phase conductor. After 120 degrees, north pole is cutting the Y phase maximum value. And after another 120 degrees, B phase. So therefore, the B phase value will be maximum after another 120 degrees, EB. Positive half cycle. Therefore, order of maximum value, first R phase, next Y phase, next B phase. Therefore, what is the phase sequence? The phase sequence is RYB. RYB for clockwise rotation. When rotor is rotating in clockwise direction, phase sequence is RYB, because first R phase, next Y phase maximum, next B phase maximum. Okay. Similarly, now let me change the direction of field rotation. I am changing the direction of field rotation. Prime mover rotation has reversed. When prime mover rotation is reversed, what will happen? Rotor will rotate in counterclockwise direction. Now rotor is rotating in counterclockwise direction. Okay, yes. Again, you consider north pole only. North pole only you consider. With respect to north pole, first maximum value is in R phase. Definitely first maximum value is in R phase. Next maximum value after 120 degrees, where it will come? After 120 degrees, north pole will comes under the B phase, rotating in counterclockwise. North pole is coming, then maximum value will be in B phase. Where north pole is there, in that conductor, EMF is maximum. So right now R phase, after 120 degrees, north pole will come to here. Therefore, next maximum value is in B phase. And another next maximum value, right now, north pole is under B phase. Another 120 degrees, north pole will comes under the Y phase. It is rotating like this. First R phase, B phase, Y phase. R phase, B phase, Y phase. So next maximum value is Y phase. So this is for counterclockwise rotation of the poles. When we are rotating in counterclockwise direction, that is the phase sequence RBY. Okay. And You can observe here one thing. If you rotate field in clockwise direction, RYB, if you rotate poles or field in counterclockwise direction, phase sequence is RBY. And phase sequence is reversing, yes. Phase sequence depends on the field rotation. This is observed from the diagram. Now, let us change the field current. I have changed the field current. Polarities are reversed. DC excitation polarities minus plus. So for that, what is the current direction? Current direction is reversed. Based on the current direction, earlier this top pole is acting as a north pole, but now it will become south pole, south pole, south pole. But bottom one becomes north pole. Bottom one becomes north pole. Reason is current direction has reversed. Current direction is reversed. Okay. But let us take the analysis or observation with respect to north pole and a positive maximum value. Positive maximum value. Okay. See, right now the north pole is not under the Y phase, not under the B phase. If you rotate this rotor in clockwise direction, when rotor in clockwise direction is rotating like this, now tell me, first north pole cuts by which phase? First north pole will comes under the B phase. So first maximum value will be in B phase. First it will comes, north pole is rotating in this. So first it will come to B phase. It will cut the B phase. So first maximum value is in B phase. First maximum value is in B phase. And after another 120 degrees, right now north pole is here. After 120 degrees, north pole will comes under the R phase. Therefore, next maximum value will be in R phase. And another 120 degrees. Right now it is under R phase, north pole. North pole only you consider. It will comes under the R phase. Lastly, it will comes under the Y phase. Okay. Y phase. And again, after Y phase, it will comes under the B phase. Dear student, it is very simple. I think on this, north pole is there. Now first north pole comes under the B phase. After 120 degrees, it will comes under the R phase. Another 120 degrees, it will comes under the B phase, Y phase. Again, after not only 3 half cycles, I am not drawing the waveform. I hope you understood this. I am directly writing. B, R, Y, again after Y, again B will come. Yes, B, R, Y, again B will come. There are not only 3 half cycles, keep on generating. B, R, Y, keep on coming. Fine, yes. But instead of, this is B, R, Y is there, na? Yes. But instead of B, R, Y, I can write this is equal to, instead of B, R, Y is also same. That is also same as RYB. BRY can be written as RYB. Reason, I just want to compare with R phase. First earlier taken R as a reference, now also R phase. BRY is also same as RYB. Are you getting my point? Yes, students, see here. BRY is there, na? BRY. Just a minute. See. So this is BRY. Again BRY. Keep on coming. BRY, keep on coming. If you start from any letter, if I start from BRY, then phase sequence is BRY is also same as BRY, also same as RYB. If you start from Y phase, it is also same as YBR. All meanings are same. In other words, what is the phase sequence? This is BRY is equal to RYB. If you start from R phase, RYB. If you start from Y phase, it is YBR. So BRY, if you start from R phase, it will be RYB. The examination, why I am saying examination, he won't start with R phase. He may be started with any phase. Okay. Next, I hope, are you getting? BRY, BRY, again BRY is coming. If you start with R phase, what is going to be happen? RYB. If you start from Y phase, it will be YBR. Sequence is same. Sequence won't change. Okay. So therefore, this is for clockwise direction. Clockwise direction. Okay, clockwise. Now, I hope this point is clear for you or not. Yes, BRY. I'm explaining. BRY is same as RYB. If you start from Y phase, it will be YBR. Okay. Now rotate in counterclockwise direction. Let us see. Lastly, counterclockwise direction. I am rotating in counterclockwise direction. Rotate rotor in counterclockwise direction. When it is rotating in counterclockwise direction, I will come to the conclusions later. Tell me now, in which phase maximum value first? In which phase first maximum value? The first maximum value will be in Y phase. First maximum value is in Y phase. Y phase. Next will be north pole is coming up, rotating counterclockwise. North pole first comes under the Y phase. Next it will comes under the R phase. Next it will comes under the B phase. And again it will be comes under the Y phase. YRB, 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 YRB. Whereas YRB is also same as RBY. You start with this. YRB is also same as RYB. Correct? Instead of taking YRB, I will take RBY. So this is counterclockwise direction. Is a counterclockwise direction. Okay. Now let us observe. In all cases, in all four cases, what was happened? Phase sequence. I am comparing first case and second case. Dear students, see. First case, for clockwise direction, phase sequence is RYB for clockwise direction. And if you rotate in counterclockwise direction, field is RBY. So therefore, phase sequence is changing. Similarly, second case also, clockwise direction RYB, counterclockwise direction RBY. This depends on the field rotation. One thing it is observed that phase sequence depends on the field rotation. Yes. Now, is it depends on the direction of field current? Tell me by observing these four conclusions. Is it depends on the field current? Let us check. I am taking rotation same. If you take clockwise and counterclockwise direction, both clockwise and clockwise direction, right? For clockwise direction with this field current, first case, with field current RYB, after changing field current also RYB. You take clockwise rotation. Are you getting? You take rotation is clockwise direction, but with that field current, first field current also RYB, after changing field current also RYB. Though you change the field current, okay, phase sequence does not depend on the direction of field current. Phase sequence does not depend on the direction of the field current. Even you observe for counterclockwise direction. I am going to write all these conclusions. For counterclockwise direction also, for first case, it is RBY. With that field current RBY, even after changing also it will be RBY. So no change. As long as rotation is same counterclockwise, whether field current may be first one or second one, after changing, there is no change of phase sequence. So from these two inputs are there, we have seen four possibilities will come. The doubly faded, okay, two inputs we are changing, four possibilities. From that, it is observed that phase sequence depends upon only field rotation. Phase sequence depends upon the field rotation. Phase sequence does not depend on direction of field current or field polarities. Phase sequence does not depend on the direction of the field current. Okay. So then tell me, what is your answer? What is your answer? Your answer is A, by changing the direction of field rotation. Answer is A only correct. B bit, by changing the direction of field current, no, does not depends upon, does not depends. Okay, answer is A. Now you may raise a doubt. Sir, you have given small question, this big explanation. Not only that, we are going to see this all conclusions I will write. Based on that, we are going to see other questions. Now, let me ask, if it is field is stationary, say, field is stationary, poles are fixed to the stator, armature is rotating. When armature is rotating means field rotation is not possible. Field rotation is not possible. A option cannot exist. If I take armature, poles are stationary, armature is rotating, poles are fixed to the stator means you cannot change the field rotation. Then you can change armature rotation. Then phase sequences depends upon what? Phase sequences depends on the direction of field current or armature rotation, direction of armature rotation, or both. That also will become another question. Now let us verify that. If I will change the armature rotation, what is going to be happen? Phase sequence will changes or not? Yeah. After observation, I will write all conclusions. The conclusions, with that conclusions, any question you can answer. So that question is over. Answer is A. I am continuing the conclusions. So for example, I am taking with the rotating armature. This is the stator, say. Poles are fixed to the stator. Earlier poles are rotating, na? Yes. But now poles are fixed to the stator. Armature is rotating. Armature is rotating. See, this is north pole. Yeah, this is north pole. DC excitation is given. Say this is acting as a north pole, and these are the three phases. Say this is north pole and this is the south pole. R phase is kept here, Y phase is kept here, P phase. This is R phase, say R phase. This is B phase. This is Y phase. Y phase conductors, armature conductor. Now I am rotating this rotor in clockwise direction. With the prime mover, I am rotating in clockwise direction. For example, I will give this much diagram only. What will be the phase sequence? The questions can be asked 4 ways, dear student, 4 ways. I will give the diagram. Options I will give: A bit phase sequence is R by bit, B bit R by, C bit B R by, like that. What is the phase sequence for this diagram? Here armature is kept on the rotor, but earlier armature was kept on the stator. This is the rotating armature. Rotating armature, stationary field. Rotating armature. Armature means conductors. Conductors. Stationary field. Stationary field or poles. Stationary field, poles. Earlier one reverse. Poles are rotating. Armature is kept on the stator. Yeah, tell me now. If I rotate in clockwise direction, see, dear students, if I am rotating in clockwise direction, can you tell me which phase first induced EMF is maximum? North pole you take, with respect to north pole, positive maximum value. From beginning onwards, I am taking only positive value. So when you are rotating rotor, right now R phase is under the north pole. So first maximum value will be in R phase. R phase. First maximum value R phase. Next, Next, which phase will comes under the north pole? Which phase will comes under the north pole? Y phase or B phase? Y phase will come after 120 degrees. This is R phase now, rotating. R phase is going after 120 degrees. Which phase will comes under the north pole? That is important. Y phase will come. Y phase. First R phase, next Y phase will come. Lastly, after 240 degrees, B phase will come. B phase. Okay. Your thing is, in which phase first maximum value? R phase cut. After 120 degrees, Y phase will cut. After 120 degrees, B phase will cut. So phase sequence for RYB in clockwise direction. If you rotate in clockwise direction, RYB. And rotate in counterclockwise direction. If you rotate in counterclockwise direction, what is going to happen? Counterclockwise direction, rotor is rotating in counterclockwise. R phase first. R will cut. After 120 degrees, B will comes under the north pole. So therefore B phase. B will come. After another 120 degrees, lastly, Y phase will come. Therefore, what is the phase sequence? RBY in counterclockwise direction. Okay. So, is the phase sequence depends on the armature rotation? Yes. If you rotate armature rotation in clockwise direction, RYB, if you rotate counterclockwise direction, it will be RBY. Okay. Yes. Getting first which phase is coming? Don't move your pen. Which conductor is coming under the north pole? Yeah. For example, dear students, you are completed now. I will do small modification here. See, I will do small modification. Tell me what is going to be happen. Instead of B phase here, I will want to, this is Y phase. I will do this. This is Y phase. This is B phase. What is going to be happen? Answer is same? No, answer is not same. In place of B, I am keeping Y. In place of Y, I am keeping B. Now, if clockwise direction say, clockwise direction, what is the phase sequence? R will come. After that, B will come. Lastly, Y will come. RBY is going to be happen clockwise direction. Counterclockwise direction, RYB. Based on the diagram, you have to respond. Based on the diagram, if examiner can be given like anything, in place of Y, he will keep B. In place of B, Y, R, he can keep. Anything he can keep. Okay? But earlier, whatever I have given, for that is I am writing. This is Y I have taken, this is B I have taken. If you change Y and B, again, according to diagram, you have to respond. So from this, phase sequence depends on the armature rotation. Phase sequence depends on the armature rotation. Depends on armature rotation. Direction of armature rotation. Direction of armature rotation. Armature rotation. But it does not depend on the field current. I don't want to draw. Here I have taken plus minus, na? Plus minus. You interchange this minus plus and do the same thing analysis, but there will be no change. Phase sequence does not depend on the direction of field current. Even if you change, you observe. It won't change. It depends upon only armature rotation. Now, final conclusion is like this. Final conclusion is phase sequence depends on the field rotation if a field is rotating. Earlier diagram we have taken, earlier page here. If a field is rotating, field rotation. If armature is rotating, armature rotation. But phase sequence does not depend on the direction of field current or field polarities. Right? Yes. Now, can I say phase sequence depends on the rotor rotation? Yes. It depends on the rotor rotation. Can I say phase sequence depends on the prime mover rotation? Yes. So rotating field means that will be kept on the rotor. If you change the prime mover rotation, rotor rotation also will reverse. Then field rotation is reversed. Phase sequence changes. If winding is kept on the rotor, say armature rotation is reversed. If rotor rotation reversed, armature rotation is reversed. Phase sequence changes. All meanings are same. 4 examiners will ask 4 types of wordings. 4 types of wording they will use. He will say phase sequence can be reversed by changing the rotor rotation, correct only. By changing the prime mover rotation, correct only. By changing the field rotation, correct only. By changing the armature rotation, correct only. All meanings are same. Which is rotating, it is depends on that. But it does not depend on the direction of the field current. Okay? Yeah. Similarly, one more question in the previous examination like this. Direction of rotation of synchronous motor can be reversed. Question is like this. Dear student, listen. Direction of rotation of synchronous motor can be reversed. A bit by changing the supply phase sequence, input supply phase sequence. B bit by changing the direction of the field current. C bit either A or B. D bit direction of rotation cannot be reversed. What is the answer? The direction of rotation of synchronous motor can be reversed by changing the supply phase sequence only, just like induction motor. RYB you have given, say phase sequence you change RBY. If you interchange any 2 phases, then direction will reverse. But it does not depend on the direction of the field current. Synchronous motor, if you change the field current, there is no change of direction of rotation. It does not depend on the direction of rotation, direction of field current. And the DC motor is there, na? DC motor, if you change the field current, rotation is going to be changes. But synchronous motor, direction of rotation depends upon only phase sequence. It does not depend on the direction of the field current. I am going to write all these things. Fine. Here, whether machine may be acting as generator or motor, whether the machine may be acting as generator or motor, phase sequence is related only with rotor rotation. See, general statement I am doing. Be careful. Listen. Whether machine may be acting as generator or motor, same machine can be used as a synchronous generator, synchronous motor. No? Yes, listen. In generator, if rotor rotation is reversed, you rotate clockwise, phase sequence is RYB. If you change the prime mover rotation, rotor rotation, phase sequence is going to be reverse. Similarly, in motor, you change the phase sequence because phase sequence is in our hand. Na? Yes. If you give RYB, it will rotate clockwise. You change the phase sequence, rotation will changes. In generator, if you change the rotor rotation, phase sequence changes. In motor, if you change the phase sequence, rotor rotation changes. Okay? Phase sequence is only related with rotor rotation. Whether motor or generator, phase sequence is only related with rotor rotation. Phase sequence does not depend on the direction of the field current. Okay. First, I will write all the statements. If you read the statements, remember statements, that is enough. No need to remember the diagram. Okay. After that, we are going to see some other questions. So let me write all the conclusions, whatever we have explained. Let me write. See, phase sequence of 3-phase alternator. Phase sequence of 3-phase alternator. 3-phase alternator can be reversed by changing the direction of field rotation. If field is rotating, reverse by changing the direction of field rotation, field is rotating, or by changing armature rotation, armature ante conductors, armature rotation. If armature is rotating, armature is rotating. That is phase sequence can be reversed phase sequence can be reversed by changing the direction of rotor rotation, by changing the direction of rotor rotation, or by changing prime mover rotation. Rotor rotation, prime mover rotation, both are meanings are same. Or by changing direction of rotation, or by changing direction of prime mover rotation. Prime mover rotation. Okay. But phase sequence does not depend on. Phase sequence does not depend on. Direction of field current. Direction of field current. Field current or field polarities. Field polarities. Similarly, direction of rotation of synchronous motor. Direction of rotation of synchronous motor. Rotation of synchronous motor can be reversed. By changing the by changing the supply phase sequence. By changing the supply phase sequence. The direction of rotation does not depend on. Direction of rotation does not depends on the direction of field current. Direction of field current. Direction of field current. And whether machine may be acting as generator or motor, phase sequence is only related with rotor rotation. Phase sequence is related with only with rotor rotation. Take it. We need to discuss questions. Yeah. Some of you are raising your hands. Yeah, I will come to that after this. We will see that your doubts. Before going to next topic, I will ask what are the doubts are there. Okay. Direction of rotation of synchronous motor can be reversed by changing the supply phase sequence. Direction of rotation does not depend on. So, whether machine may be acting as the machine may be acting as generator or motor. Phase sequence is only related with rotor rotation. Is only related with rotor rotation. Phase sequence no way related with. Phase sequence is no way related with field current. No way related with direction of field current. Field current is, phase sequence is no way related with direction of field current. Remember, dear students, have taken? Yes. In synchronous machine, field current least bothered. Synchronous machine field current direction is reversed, nothing will happen. Remember that. If any question, not only this question, any questions are being given, field current direction changes, nothing will happen. You can change whatever the field current you want. Machine performance is not going to be affected. Nothing will happen. Rather, DC generator is there, na? The field current direction must be proper. Field terminals must be properly connected to the armature for self-excited generator. Correct? Failure of generating voltage. But synchronous generator not like that. I will ask one question for you. Alternator is separately excited generator or self-excited? Separately excited. We are separately exciting. So field current direction least bother. Least bother. Right? Yeah. Now I am coming to the questions. Questions for you. See, the questions are like this. Question is, ER is equal to ER at an angle 0, EY at an angle minus 120, EB at an angle minus 240. These are the generated EMFs. Are you getting? Generated EMF, or first let me write the generated EMFs of three-phase alternator. Three-phase alternator are ER at an angle 0, EY at an angle minus 120 degrees, EB at an angle minus 240 degrees. Then the phase sequence is, dash. Is it RYB or RBY? I don't want to write A bit, B bit, C bit. You tell me, let us directly. RYB or RBY. Generated EMF of three-phase alternator. ER 0, EY minus 120, EB minus 240. What is the phase sequence? Phase sequence is RYB or RBY. Okay. Dear students, earlier what I have given, for example, this diagram, you compare with this diagram, this is R, no? And this is Y, and this is B. In this omega t, this is EMF waveform. This is ER, EY, EB. So which is first maximum value? Can you write the equation for these voltages? ER, EY, EB. ER is equal to, ER will be at an angle 90 degrees, na? Yes. ER at an angle 0. What is EY? Minus 120. It is lagging. Y phase lags. Y phase voltage lags the R phase. R phase is first maximum value. First maximum value means it will be 0. EY minus 120. What is EB? Minus 240. Na? Yes. X-axis is time axis, time angle. Time angle ante first R phase maximum value, next Y phase, next B phase. So R0, Y coming after, later ante lagging, minus. B lastly coming. So for this, what is the phase sequence from this diagram? RYB. Therefore, for this also, what is your answer? Answer will be RYB. Phase sequence is RYB. First R, next Y. R coming first, R maximum, next Y, lastly B. Okay, phase sequence is RYB. Similarly, yeah, let me take another question. So, Varna, this waveform already we have seen in the first page. Okay. Next question is, this is a question from ESE 2013 examination question. The phase sequence of three-phase alternator. Phase sequence of three-phase alternator is RYB. RYB given. A sequence of three-phase alternator is RYB. Okay, then A bit. Y phase. Okay. Y phase leads the R phase. Y phase leads the R phase. B bit. Y phase lacks the B phase, C bit. Y phase leads the B phase, D bit. Y phase is in phase with R and B. Tell me what is the answer. Phase sequence is given RYB. Based on this, you have to answer RYB. A sequence RYB. Then Y phase, he is asking with respect to Y phase. Y phase leads the R phase, or Y phase lacks the B phase, or Y phase leads the B phase. So what is the answer? Tell me. Chat box. What is your answer? Answer is C. Yes. Answer is C. C is correct. Exactly. Dear students, see here. Phase sequence is given. What is the phase sequence? RYB. No? Phase sequence is given RYB. RYB given. RYB given means first R phase. Next EY minus 120. EB minus 240. First R phase. When compared with RY, with respect to RY, Y lacks the R phase. Correct. Y is coming later R phase. R phase first, Y later. Later means lagging. Y phase lacks the R phase. Correct. Or when compared with Y and B, Y phase, Y leads the B phase. Both are correct. These two are correct. Y phase, if we compare, R phase to lags. Y is coming after some time of R phase, after until lagging. When compared to Y and B, Y first. Therefore, Y leads. So therefore, what is your answer? Y phase leads the B phase. C is correct answer. C is the correct answer. Yeah. Now, then similarly, let me give another question. So over. Yeah. Next question is, see. The question is, following are the phasors of generated EMFs of three-phase alternator. This is E suffix R and this is E suffix Y, E suffix B. Okay, E suffix B. This is phasor rotation. Phasor rotation. Phasor rotation is counterclockwise direction. Counterclockwise direction. Then the phase sequence is. Then the phase sequence is. Then the phase sequence is dash. What is the phase sequence? What is the phase sequence? Phasors ER, EY, EB. They are rotating. Counterclockwise direction he has given. Then what is the phase sequence? Answer? RYB, RYB. Very good. Exactly correct. Exactly correct. So in this, nothing is there. ER at an angle 0, na ER. If anything is given, it is always better you write like this. Whatever it may be given, for this ER at an angle reference, you take ER at an angle 0, you take ER at an angle 0. Then when EY is coming, EY is minus 120, minus 120. EB is minus 240. You arrange in that way, 240. So what is the phase sequence? RYB. Correct. RYB. RYB. Okay? Yeah. The meaning is, see, meaning is, phasor rotation means don't think like this. This is RBY, no. RBY, no. When phasors are rotating counterclockwise, observer must be clockwise direction. Observer identify clockwise. Or see here, an observer is there. An observer is observing here. C is the observer. Is observer and is observing like this. Is observing. According to observer, dear students, according to observer, just a minute, see. Observer is sitting here, na? When phasors are rotating. When phasors are rotating, phase sequence is nothing but the order at which phasors are crossing through him. The order at which phasors are crossing through him. So which phasor first crossing? R phase vector. After 120 degrees, which phase are crossing? Y phase is crossing. After another 120 degrees, B phase is crossing. So with respect to observer, it is like this. Remember that. With respect to observer, phase sequence is the order at which phasors are crossing through him. Phasors are crossing through him. Crossing through him. Which phasor first crossing? Next, which phasor is crossing? First R phasor. Phasors are rotating counterclockwise. So first R phase crossing, next Y phase, lastly B phase is crossing. So therefore phase sequence is RYB. RYB. Now instead of that, can I write okay. If observer is standing here, what is going to happen? Tell me. Observer can stand anywhere. For example, if observer is standing here, which phasor crosses first? Y phasor crosses. Y phasor crosses. Therefore, next B phasor, last R phasor. What I mean to say is, RYB phase sequence is also same as, if you start from Y phase, what is going to happen? YBR. RYB means if you start Y phase, YBR. Sequence, cyclical. Or that is also equal to, if you start from B phase, it is going to be BRY. All options are correct only. Sometimes how you will give, all the options are correct. A, B, C, all are correct. So that is a phase sequence. So phase sequence is, phase sequence, all these things. Phase sequence may be RYB, or that is also equal to YBR. That is also equal to BRY. You can start with any letter. Correct. No need to take one phase reference. Why I need to take ER only at an angle 0? You can take EY also at an angle 0. Na? Yes, any phase can be taken as a reference. There is no rule. Generally, we are taking R phase at an angle 0. Okay? Yeah. This is the answer. Now, I will ask one point answer for me. This is a question, na? Okay. Instead of that, I will change the phasor rotation. What is going to happen? You tell me when phasors are rotating clockwise. What is your answer? The answers are same, huh? No, answers are going to be changes. Changes. R first. Next, which will crosses? B crosses. With respect to B crosses. With respect to that, lastly, Y crosses. Phasors are rotating, then your phase sequence is going to be RBY will come. RBY. Phasors are counterclockwise direction. RYB. He is giving. You need to answer based on the diagram is given. Diagram is given. I am writing conclusions for one direction. Counterclockwise direction, I have written all the conclusions. If it is clockwise direction is given, say, now according to that, you need to respond. So let me make I am coming to again original rotation is counterclockwise direction. All this discussion is valid. Okay, I hope you understood. Clockwise is given means it is the same concept you apply. Okay. Now lastly, I will give another question. With that, you will get a clear idea. Okay. The last question is, see, the question is, phase sequence of three-phase alternator. Phase sequence of three-phase alternator. Three-phase alternator is RBY. Phase sequence of three-phase alternator given RBY. If the direction of armature rotation is reversed, the direction of armature rotation is reversed. Direction of armature rotation is reversed. Then the phase sequence will be. Then the phase sequence will be A bit, RBY, and B bit, BYR, C bit, C bit, BRY, and D bit, YRB. Yes. What is your answer? This is a question. Phase sequence of three-phase alternator is RBY. If the direction of armature rotation is reversed, then the phase sequence will be. What is the answer? Okay. Yes. So what is your answer? Yeah. C. Very good. Answer is C. You are correct. Let me write RBY is given. Na? What is the phase sequence is given? Phase sequence is given RBY. RBY is given. When RBY is given, if the direction of armature rotation is reversed, if the direction of armature rotation is reversed, then the phase sequence will reverse. then the phase sequence will reverse. Correct? Yes. Phase sequence will reverse. Therefore, what is the phase sequence? Phase sequence is RYB. If it is RBY is given, our immediate answer is RYB. RBY is there, it is reverse, RYB. But that is also equal to, can I write YBR? Yes, YBR also correct. If you start from Y phase, YBR, and if you start from B phase, it will be BRY. All these are correct. All these are correct. All are correct. All are correct. Okay, yes. But he has given only which is suitable answer, BRY. BRY. So C is your answer. C is your answer. Then he has started with R phase, but options he has not started with R phase. Different phases it may be. But whatever it may be given, yeah, they are the answers. Okay. Right. In the same question, dear students, see, in the same question, I may ask question like this. How? If direction of is over, na? Okay, listen. In this question, if the direction of field rotation is reverse, what is your answer? Answer same. Armature rotation means if it is field is rotating, field rotation. If you change the field rotation, also answers are same. Rotor rotation also same. Prime rotation is reverse, answer is same. But if field current direction is reverse, what is your answer? No change of phase sequence. RBY only answer. Correct? Yes. Phase sequence is not going to be changed. Yes. That is only the thing. Okay? Here I have given question based on the armature rotation. Instead of that field rotation also I will give. That is, it is understood that our alternator is said to be rotating field. Rotor rotation, all meanings are same. Okay. So with this, we are completed our phase sequence in total. Phase sequence is total, right? Yes. So we have seen what is the definition of the phase sequence. What is the definition of phase sequence? Field current reverse, what happened? Armature rotation reverse, what happened? Fine. And the questions may be started with any letter, or question may be given in the form of waveform, or question may be given in the form of phasors also, equation also, anything. Now you are having 100% information with you regarding the phase sequence, right? The subject can be actually learned by the question. If a question is being given, your attention is different. That's the reason I will prepare you people by giving questions. We can learn the subject by seeing the questions. Okay. Yeah. Fine. Right. So before going to the next topic, if some of you people are raising your doubt, raising your hand. So what is your? Please raise your hand in this topic. Any doubt is there? Phase sequence. Any doubt is there? Please raise your hand. Please raise your hand. Nitish Kumar. Nitish Kumar, do you have any doubt regarding this?
No doubt, sir.
Some of you people are keep on raising their doubts, hands, so therefore I am getting disturbed. Are any doubts are there, please? Anyone?
Hello, sir.
Tell me.
Sir, in this phase sequence, I understood all, but they will ask something like that, in that lagging only, they will ask about a degrees method, 120 degrees lagging, which is 120 degrees lagging.
Yes.
120 degrees lagging. In
Yeah,
that type, I have some problems, sir.
What is the problem? In the diagrams, whatever I have given,
No, sir. Generally, I'm asking.
See, R0, y minus 120 means y lagging. If y plus 20 is given means it is going to be leading again. Even, for example, R0, y plus 120 given, instead of plus 20, I will write minus 120. You draw a phasor according to that. You draw a phasor, okay, and whatever we have applied, you just follow that.
Okay, sir. For that, we want to select one reference, na sir, first.
Yes, reference, the reference you need to select, but options, based on the options, which option is suitable, that we have to select. Options can be started anywhere. For example, I may start with R phase, or some other may start with Y phase. Whatever it may be, even if you take any angle, reference can be anything. But here, ER at an angle 0, na? EY at an angle minus 120, say, minus 120. EB at an angle minus 240. Okay. For this phasor, ER, and this is EY. Just a minute. Phasor. This is ER. This is EY. And this is EB. Phasors are rotating counterclockwise, na? Yes. If I take EY at an angle 0, tell me. If I take a EY at an angle 0, then tell me after that, what about EB? EB minus 240. EB minus 240. ER will be, what about ER? No, sorry. EB will be minus 120. EB minus, are you getting this point?
Yes, sir. Yes, sir.
If I start from Y phase, say, EY at an angle 0, say, EB minus 120. But ER will become plus 120, leading plus 120 or minus 240. Both are same. ER minus 240. If the phase sequence changes, no change. No change. Anyone you can take reference.
So, if we take B as a, here we took R as reference. If we take B as reference, we will get another degrees, another angle.
No. For example, phasors are given. You take a phasor and a phasor rotation is given. Na? Any phase you take, verify that you will get answer is same. Starting point may be different here. Starting point may be you are taking Y phase reference, it will start from YBR. Instead of that, if you take B phase reference, it will become B RY.
Okay, sir.
Like that. You just draw the diagram and if you take R phase reference, you check it. Instead of that Y phase reference, you check it. B phase reference, you check it. Answers you will get same. Provided that vector rotation must be taken same counterclockwise direction. Any phase you take reference, answer is not going to be changes.
Okay. Understood, sir.
Yeah, you can ask. If any doubts are there, please you do at the same time. I will give my number also 9849719672. My WhatsApp number is also there. You try for that. If you are getting any doubt, right? You can also you can raise. No problem. Okay.
Okay, sir. Okay.
This is the concept. It will be valid for whatever you take. Right now you may be having, but once you practice that, we are going to realize it will be same. Okay. Right.
Okay, sir. Okay.
Yeah. Next, anyone? Bashchan ready. Sai Charan ready. Hello.
Sir, I only asked, sir, now.
Okay. Over, na? Yes.
Oh, over, sir.
Yeah. Fine. I hope this is same. If any doubts are there, you can ask. No problem. Later. Now let us move to the next topic. Next topic we are going. Okay. Coming to the next topic. Yeah. Next topic is magnetic drag. Magnetic drag. Magnetic drag. Magnetic drag. This magnetic drag concept is same for all generators. It's not only for alternator. Every generator, magnetic drag concept takes place. What is magnetic drag? Magnetic drag is nothing but electromagnetic torque opposition in generator. Electromagnetic torque opposition generator. You may be knowing that. In generator, motor action takes place. In motor also generator action takes place. Correct? It may be motor or generator. In motor, generator action takes place. That is back EMF. And generator also motor action takes place. Two actions simultaneously exist. Two actions simultaneously exist. But in motor, generator action means what? In motor, generator action means what? Back EMF. Back EMF. And in generator, also motor action takes place. Let us see how it is. Let us see how it is. See, this is my rotor. Poles. Okay. So north pole, south pole. Flux direction is north to south. And I am taking two conductors. The flux direction is north to south. Let us take two conductors. I am taking this one conductor and this is another conductor. The rotor is driven in clockwise direction by using the prime mover. The prime mover. By using prime mover, we are rotating in clockwise. Clockwise. Yes. See, this is the generator. I am rotating in clockwise means force due to prime mover in which direction? Upwards direction. This is force, FPM. The prime mover torque clockwise, na prime mover torque clockwise. Rotation is in clockwise. Rotation is in clockwise. So force due to prime mover, upwards direction. Force due to prime mover, downwards direction. The force due to prime mover is downwards direction. Torque is nothing but rotating force. Torque is nothing but rotating force. So rotor is rotating in clockwise. Rotor, this is prime mover torque, na? Yes. This is TPM. Rotation is in clockwise direction. Clockwise direction. F suffix PM means force due to prime mover. Tangential force. Torque is nothing but rotating forces. So conductor rotor is rotating in clockwise. For that, what is direction of induced current? Apply your right hand rule. In this conductor, see, in this conductor, first conductor is there, na? It is moving upwards. Other conductor is moving downwards. Downwards. So apply your right hand rule. Right hand rule. The first conductor, four-finger flux direction. Because these are the flux direction. Flux direction is in this. This is a flux direction. Flux. So based on that four-finger flux direction, motion of the conductor. Current is inwards. Current is inwards. Cross. It is cross. First conductor cross. Whereas here it is dot. Flux direction, motion of the conductor. Dot. Dot. In this it is dot. Generated EMF. And when EMF is there, load is connected, it will drive the current. First generated EMF, then load is connected current. This is the current say. EMF and current direction is same say. And the EMF and current both will be, current directions are same. In which direction EMF, current also will be the same direction. So once these are the conductor, but these conductors are not ordinary conductors. What are they? They are current carrying conductors. These are the current carrying conductors. How current came? Generator action. Dear students, first generator action, it is rotating, it is cutting the flux, EMF is induced, and when load is connected, it will drive the current. So by generator action, current is coming, and the current carrying conductor exists in magnetic field, it will experience a force. Motor action takes place. First generator action followed by motor action. Due to generator action, current is coming, current conductor exists. According to Lorentz force law, when current carrying conductor exists in magnetic field, it will experience a force. Torque will be developed. But the torque can be found by applying the Fleming's left-hand rule. What Fleming's left-hand rule indicates? Forefinger flux direction, forefinger flux, right? Center finger direction of current, then thumb indicates direction of force, Forefinger flux, right? Yes. Center finger current, thumb in this direction. So therefore, let me apply forefinger flux direction, center finger current, thumb is downwards. This is force. What is that force? Due to motor action. And this is force due to motor action. You need to apply left-hand rule to find the force. FM, motor force. Cross. And this is dot. Counterclockwise direction. FM upwards downwards means, here students say, this is upwards, this is downwards. Which direction it will rotate? Counterclockwise. Torque is counterclockwise. So electromagnetic torque is in counterclockwise direction. That is in opposite direction of the field rotation. TEM is in opposite direction that of field rotation. So this electromagnetic torque is called braking torque. Electromagnetic torque or braking torque or counter torque. You can say counter torque. It is causing braking action. Yes. Braking torque or counter torque. And this electromagnetic torque opposition is called a magnetic drag. This electromagnetic torque opposition is itself called magnetic drag. Magnetic drag and torque opposition in generator is called magnetic drag. It is dragging the rotor, opposing. It is opposing the rotation, dragging the rotor, magnetic drag. And this electromagnetic torque only load torque. Because electromagnetic torque is proportional to current. Load condition only current exists. When alternator generate EMF, but no load condition, no current, no torque. When loaded, then it will drive the current, and the torque is proportional to current. So load is electrical load. That's the reason torque is electromagnetic torque. This torque only load torque I can say. But that opposes always electromagnetic torque in generator opposite direction that of the prime rotation. Whereas in motor, torque will be same direction that of rotor rotation. Motor like the torque is same, but generator torque opposes. The torque, this is every generator same. Okay. And this torque is itself I am going to represent in equivalent terms of electrical power developed. First, let me write the conclusions. In generator, in motor, generator action takes place. In motor, generator action takes place. That is back EMF. That is back EMF. Okay. And how direction of back EMF can be found in motor? By applying right hand rule only. EB in motor can be found by applying Fleming's right hand rule only. It is induced EMF. Correct or not? Motor low back EMF. First motor action it will rotate, then it cut the flux, induced EMF. That EMF, back EMF. Back EMF in motor can be found by applying Fleming's right hand. Similarly, in generator, of course, we are discussing about generator. In generator, also motor action takes place. Generator also motor action takes place. Motor action takes place. Motor action takes place. Because that is, what is the motor action? Whenever a current carrying conductor, whenever a current carrying conductor exists, current carrying conductor exists in magnetic field, current carrying conductor exists in magnetic field, it will experience as a force. Magnetic field, it will experience as a force. Experiences a force or torque. A force or torque. The direction of torque can be found by applying the right hand rule. The direction of force or torque can be found by Fleming's left hand rule, not right hand rule, Fleming's left hand rule. It is a generator, but I am applying my left hand rule to find the torque. Torque can be found by left hand rule. Generator by right hand rule. It is a motor or generator. Some students blindly they will say right hand rule is only for generator, left hand is only for motor, not like that. Right hand is for induced EMF. Left hand rule is for torque. So motor also torque is developed. The torque can be by Fleming's left hand rule. Generator also torque is developed. That can also be found by left hand rule. I have applied left hand rule only here to find the torque. FPM is prime mover torque clockwise, but motor torque counterclockwise. So Fleming's left hand rule is found by Fleming's left hand rule. And we know what is the Fleming's left hand rule. Fleming's left hand rule is, Fleming's left hand rule. What is that? If forefinger indicates direction of flux, center finger indicates direction of current, then thumb indicates direction of force or torque. Thumb indicates direction of force or torque. So we applied our left hand rule. Okay. First, I have, dear students, there is no confusion in this diagram, earlier diagram. FPM, upwards, downwards. First, I have applied right hand rule to find the induced EMF. Right hand rule induced EMF, that is cross. Generator action, first current is coming cross. After current is coming, then I am applying left hand rule to find the torque. To find the left hand rule, I am applying to find the torque. Okay, right hand rule, I have both hands I was applied to find the current, right hand rule, torque left hand rule. But the torque is in which direction? Opposite direction. The electromagnetic torque developed. The electromagnetic torque developed. The electromagnetic torque developed. TEM developed in generator. Generator is always in opposite direction. Generator is always in opposite direction that of prime mover torque. That of prime mover torque or TPM. That of TPM or rotor rotation. Rotor rotation. Opposite direction that of prime mover torque or rotor rotation. That's the reason this TEM. That's the reason TEM is called braking torque or counter torque. Braking torque or counter torque. Braking torque or counter torque. Counter torque. This TEM opposition, this TEM opposition is called magnetic drag. Is called magnetic drag. Electromagnetic torque opposition only, magnetic drag. And this electromagnetic opposition TEM, the TEM can be represented in equivalent, electrical power developed in terms of, equivalent power developed. In terms of equivalent power developed. Equivalent electrical power developed. Electrical power developed. Electrical power developed. Okay. Because in every rotating machine, torque balance equation takes place. Because in every rotating machine, energy balance, power balance, and a torque balance takes place. Torque balance exists. Every rotating machine, energy balance, power balance, and torque balance exist. Energy balance, power balance, torque balance exist. According to energy conservation, energy neither created nor destroyed. Energy balance equation takes place. Power balance also. Energy means what? Power into time. As long as energy is taking place, power is there, power multiplied with time energy. And where power is there, torque also exists in a rotating machine. Power is equal to torque into omega. So therefore, you can write in terms of energy, you can write in terms of power, you can also write in terms of torque. All they do exist simultaneously in rotating machines, everything exists. But you can talk in terms of torque, you can talk in terms of power, some other will talk in terms of energy. But all they do exist simultaneously. Okay. So, the energy torque balance equation, mainly we want to focus on torque balance equation. Torque balance equation in generator, prime mover torque is equal to J into d omega by dt plus B into omega plus TEM. That is, this is first one, J, moment of inertia. J is the moment of inertia. B is the frictional coefficient, friction coefficient. The first one is inertia torque, Ti. This is frictional torque, T suffix B I am taking. This is electromagnetic torque. So this is a torque balance equation. Torque balance equation in generator. Torque balance equation in generator. Okay. Yes. J is the moment of inertia. Na? Moment of inertia. B is the friction coefficient. Correct? Yes. Friction coefficient. So G d omega by dt is itself inertia torque. B into omega is a frictional torque that is proportional to speed T. But all these three torques opposes the prime mover torque. opposes the prime mover torque. If I draw the diagram, it would be like this. This is the prime mover. Prime mover is a generator. And generator is loaded with some resistive load or any type of load, say load. Okay, yeah. I am rotating my prime mover in clockwise direction. See, we are rotating our prime mover torque clockwise direction. But inertia torque will be in opposite direction. The three torques opposes. Correct or not? Inertia opposes the rotation. To overcome inertia, some prime mover torque is required. Inertia torque. And also frictional torque, T suffix B, also opposes. Electromagnetic torque also opposes. All three torques in opposite direction. Okay, load torque opposes. Where friction is there, friction also opposes the rotation. To overcome that friction, some extra prime mover torque is required. Inertia also opposes. Like a traction, electric traction, if you take, inertia torque is much more. Traction weight is much more. Inertia torque is itself 4 times that of the load torque. Yes. So all three torques oppose. So the duty of the prime mover torque is it has to be overcome all these oppositions. Torques opposes. Thereby what happened? And this will generate EMF. And EMF will be generated. This is E, say generated EMF that will drive the current. Armature current. Drive the armature current. So due to that, we are giving mechanical power here. This is mechanical power input we are giving at the prime mover. Now we are getting electrical power output. What is electrical power output? E into IA. Generated EMF into current. That is electrical power output. Mechanical power means TPM into omega. Whereas this electromagnetic torque. But electromagnetic torque is proportional to flux into current. But that is proportional to current. That is itself load. That's the reason electromagnetic torque is called load torque. TEM is proportional to load. Electromagnetic torque is proportional to load. Right? Proportional to load. If load is connected, fine. Load condition only current exists. Na? If I remove load, what is going to happen? No load condition. Is there any current? No current. No current, no torque. Exist only during load condition. Okay. 3 torques opposes. But inertia torque exists only during starting. No? Inertia torque exists only during starting. Under steady state condition, inertia torque will be 0. Inertia torque exists only during starting. At 0 speed, inertia is more. Our generator starting from 0 speed onwards. Na? At 0 speed, inertia is more. As speed increases, 100 RPM, say inertia reduces. 200 RPM, 300 RPM. The machine will be gradually reaches to its final speed. As speed increases, inertia will be reduced. But once it reaches to steady state speed, once the machine is reached to steady state speed, synchronous speed, speed is constant. When constant means what is omega constant? D omega by dt 0. Therefore, inertia exists only during starting. Once started, inertia torque is 0. Inertia torque is 0. Let me write that. Inertia torque, Ti, exists only during starting. Exist only during starting. But under steady state condition, omega constant. Omega means what? 2 pi n by 60. Dear students, omega is nothing but angular speed. Omega is equal to 2 pi n by 60. Omega is constant. When omega is constant, what is Ti? Inertia torque is equal to J d omega by dt. That inertia torque is 0. Inertia torque is 0. When inertia torque is 0, which torque exists? Now prime mover torque is equal to only B into omega plus TEM. Frictional torque under steady state condition, only frictional torque and electromagnetic torque only exist. Friction torque and electromagnetic torque. Steady state condition. Okay. This equation is under steady state. Steady state condition. Steady state condition. Okay. Now you multiplied on both sides with omega. For the torque multiplied with omega, it becomes power. I am multiplying TPM into omega is equal to B into omega square plus TEM into omega. Multiply with omega. TPM into omega, that is equal to B into omega square plus TM into omega. Then it becomes power, na? TPM into omega is nothing but this is the mechanical power input. TPM, prime mover torque into omega, mechanical power. But this is a power loss, mechanical losses. Mechanical loss, frictional loss. Mechanical power loss and frictional loss. Friction loss is mechanical power loss. Na? Then what is this? This is electrical power developed. Once you have given mechanical power, some power is wasted in the form of frictional losses, mechanical losses. Then rest of the power is electrical power. Therefore, by comparing here, therefore, electrical power developed is equal to what? This is PE. That is electrical power developed. Therefore, electrical power developed. Electrical power developed. PE. PE is equal to TEM into omega. TEM into omega. That is also, can I write is equal to E into IA? Yes. Torque into omega also same and generated EMF into current also same. Same. Right? Electrical power developed. And then what is electromagnetic torque? Electromagnetic torque is equal to PE divided by omega, or that is E into IA divided by omega. Omega. Okay. Electromagnetic torque. Generator. Electromagnetic torque generator. Similarly, taken this TEM, P into omega, that is E into IA by omega. You want to, sometimes you will ask in generator, calculate the torque developed in generator means induced EMF into current by omega. If power factor is there, E into IA into cos phi. Cos phi also we can take. I have taken resistive load. That's the reason simply it is E into IA. Power factor is equal to 1. Otherwise, AC currents say E into IA cos phi by omega. EI cos phi by omega. That is the power. Electrical power developed. PEM. Next, see. And here, the electrical power developed can be represented in equivalent terms of electrical power developed. Torque TEM is represented in equivalent power developed. Next one, see. Under steady state only I am taking TPM is equal to B into omega. TPM is equal to B into omega plus TEM. Okay. Yeah. Now, omega is equal to what? TPM minus TEM by B. Remember that this relation. TEM, omega is equal to prime mover torque minus electromagnetic torque divided by B. So speed is depends upon what? Prime mover torque and electromagnetic torque. Prime mover torque and electromagnetic torque. Those who are talking about the speed, you need to discuss with this equation. Then only that is valid. For example, I will ask a question. When load increases on the alternator, dear students, when load increases, TEM increases. Na? When load increases, TEM increases. When TEM increases, speed will reduce. But to maintain the same speed, what to do? Prime mover torque also has to be increased. When load increases, electromagnetic torque increases. Opposition. But to maintain the same speed, you have to increase the prime mover torque also you need to increase. Load want power. Ultimately, load want power means from where the power should come? Input. So TEM is nothing but load torque. When load increases, current increases, electromagnetic torque opposition increases. But to maintain the same thing, speed, prime mover torque also has to be increased. See, under no load condition, let us take. For example, under no load condition. Under no load condition, what is the current? IA0. IA0 means what is electromagnetic torque? 0. Electromagnetic torque 0, then prime mover torque is equal to only simply B into omega. Because current 0 means TM 0, B into omega. Multiply with both sides, TPM into omega is equal to what? B into omega square. This is mechanical power input is equal to what? Mechanical losses. TEM is 0. No load condition. Open circuited. Load open circuited, current 0. TEM 0. Which torque exists? Only prime mover torque and frictional torque. In other words, from this what we understood, under no load condition, the mechanical power input is given only to meet the losses. Machine rotated synchronous speed only. Under no load condition, the mechanical power input given, P mechanical input given is only to meet the mechanical losses. Right? Yes. But as load increases, what will happen? But when load increases, same continuation of this. When load increases, okay, current IA increases, TEM increases. Then to maintain the constant speed, TPM also has to be increased. Has to increase. Huh? Yes, omega is equal to TPM minus TEM divided by B. So when you are increasing TEM, TPM also must be increased. Then speed will be constant. Both has to be increased. Right? Okay. Now this is about electromagnetic drag. Only important thing is some student, they will raise a doubt. Listen, dear students, they will raise a doubt like this. Sir, this electromagnetic torque opposition, is it a advantage or disadvantage? Tell me, what is your answer? Your friend is asking, yes, in generator, electromagnetic torque is opposing unnecessarily. That is a disadvantage. I will try to avoid that electromagnetic torque opposition. What is your statement? What is your conclusion on this? See, dear students, electromagnetic torque is not a disadvantage or not advantage. It is a part of the principle. Part of the principle. When alternator is there, you are rotating. When alternator is there, you are rotating. It is cutting the flux. EMF is induced. And when load is connected, it will drive the current. When current is coming, torque opposition will comes into picture. That you cannot avoid. It will take place. It will take place. If you don't want electromagnetic torque opposition, means no load. It will be no load. Are you happy with no load? No. Compulsory. I have to apply the load, and then electromagnetic torque opposition will come. Fine. And prime mover torque exists, both exist. Prime mover torque will be there, electromagnetic torque will be there. Electromagnetic torque is load torque. Electromagnetic torque is itself load torque. If you don't like, means you operate your no load condition. But what is the use of alternator operating no load condition? Therefore, when load connected, automatically torque will comes into picture. And these two torques, prime mover torque and electromagnetic torque, both will be balanced. Machine will rotate at synchronous speed. Only thing is, when load increases, your prime mover torque also has to be increased. No load condition, how much prime mover torque is enough? Just 5%, 10% is given, that is sufficient. No load condition, prime mover torque is only to overcome the frictional torque. How much friction torque? 5% to 10%. Small amount of mechanical power or mechanical torque is given sufficient. But load condition, you have to give rated mechanical power input, rated mechanical torque, because electromagnetic torque also rated. Fine? Yes. So load torque, electromagnetic torque itself load torque. That opposition we are calling magnetic drag. Fine? This takes place in every generator. It is not only synchronous generator. It takes place DC generator also torque opposition, motor induction generator also torque opposition. Every generator torque opposition takes place. But I need these equations. We are going to see all time that equations. Whenever you are talking about the speed, you have to talk with this equation only. Omega 100, of course, 2 pi n by 60. That equation you have done. So just have an idea about this, right? And this equation keep on coming till the end. Okay. This is about electromagnetic torque opposition. Now let us take the break. After the break, we are going to start another important topic, dear students. Important topic, construction of alternators. We'll start with construction of alternator. Therefore, take the break for 20 minutes. After that, I am going to start construction. Very, very important topic. So take the break. Take break for 20 minutes. 20 minutes. After the break, the topic is construction of alternator. Construction of alternators will be discussed. Very important topic. So class will start when? Now it is around 7:35. 7:35 means 7:55 will start. Okay. Take the break and then come back. Important topic, construction of alternator is going to be started. Yeah, welcome back. The next topic is construction of alternators. Are you ready? Yes. The most important topic in most of the examinations, you can get at least one question on construction of alternators. Construction of alternator, and that to be without having clear idea about the construction of alternators, and we cannot continue the next coming topics also. Okay, basic thing. Let us see construction of alternator. I hope all of you have joined. Fine, good. Okay. Construction of alternator. Construction of alternators. Alternator is a rotating machine. Alternator is a rotating machine. Every rotating machine will have two main parts. Two main parts. The main parts are stator and rotor. One is stator, like every generator and motor will have two main parts. Number one, stator, and another one is rotor. Stator and rotor. Stator and rotor. And again, there are two types of rotors. Stator is same, but two types of rotors. Two types of rotors. One is salient pole rotor. Salient pole rotor. Another one is cylindrical rotor. Cylindrical or non-salient pole rotor. It is cylindrical rotor. Cylindrical rotor is also called non-salient pole rotor. Non-salient pole rotor, or can also be called as round rotor. Round rotor. Two types of rotors, but stator is same. Salient pole rotor, cylindrical rotor, non-salient pole rotor. So based on the rotor construction, there are two types of alternators. Stator is same, but if you use salient pole rotor, alternator is said to be salient pole rotor alternator. If rotor is cylindrical type, cylindrical rotor alternator. So based on the rotor construction, two types of alternators. Number one, salient pole rotor alternator. Salient pole rotor alternator. Second one is cylindrical rotor alternator. Cylindrical rotor or non-salient pole rotor alternator. So there are two types of alternator based on the rotor construction: salient pole rotor alternator and cylindrical rotor alternator. Yeah. Can you tell me, first of all, why to have two types of alternators? Why salient pole alternator is required? Why non-salient pole rotor alternator is required? Only one alternator is there. Our syllabus is going to be less. We are more comfortable. Fine. Why to have two types of alternator? These two types means, first one, salient pole alternator is suitable for low speeds. Low speed alternators, cylindrical rotor high speed. Salient pole alternators are suitable for some power station. like hydro power stations, Elliott core only suitable. Steam power stations, thermal, nuclear power station, high speed they are. Cylindrical rotors must be cylindrical to withstand high speed. Okay, that we are going to see. First, let us start with construction of stator. Stator is same for both two types of rotors. Let us see one by one. Stator, after that rotor. So, construction of stator. Stator. Stator is hollow cylindrical in shape. Circular shape, na? Stator is in circular shape. Hollow cylindrical in shape. This is a stator. Yeah. It will have some length, na? Yes. The stator. Inner periphery is slotted. The inner periphery slots are made on inner side to accommodate the armature winding. Stator. Like entire periphery will be slotted. Slots are made on total inner periphery. These are the slots. Entire inner periphery is slotted. Slotted means we will cut that portion. Correct? Slots are made. In that armature windings will be kept. Slots. Slots means actually how it will be. They are going to be like this. Better. You cut this portion. Slots can be made. In that armature winding is kept. Armature winding. Armature winding, for example, if you take one particular coil, so one side of the coil, if one side of the coil is kept under the other side of the coil, is armature coil. Armature coil. One coil. To take second coil. Of course, so many coils will be there. They are distributed. These are the armature coils that are placed on the stator core. Stator core. Armature winding is placed. This is the stator. Inner periphery is started to accommodate the armature winding. Okay. Stator is made stator. Inner periphery is started. Inner periphery is started to accommodate the armature winding. To accommodate the armature winding. Armature winding is placed in the slots made under the inner periphery. And the stator core is made with. This is a stator core, na? Yes, this is a stator core. Stator core is made with. Stator core is made with. cold rolled non-oriented steel. Cold rolled non-oriented steel. Cold rolled non-oriented steel with 3% silicon. 3% silicon. That is said to be silicon steel. Stator is made with silicon steel. Silicon steel and laminated. It must be laminated. Silicon steel and laminated to reduce the eddy current losses. It will be laminated to reduce eddy current losses. Okay. The stator core is made with cold rolled non-oriented steel. Non-oriented steel with 3% silicon. That is nothing but silicon steel. It's made with silicon steel and laminated to reduce the eddy current losses. Cold rolled non-oriented. Where is the oriented steel is used? Transformer. In transformer, you are going to made with how? Core is made with CRGO. Is made with a cold rolled grain oriented. That will be only in transformer. Except transformer, all they will be non-oriented steel. Orientation is favorable only for linear cores like transformer is there, na? I think you are completed already. Transformers, all the grains will be oriented in a particular direction. Along with that, if flux is passing, your reluctance is going to be reduced, right? But whereas circular shape, orientation is not favorable. Orientation is not possible, not favorable, right? Orientation is not favorable. Orientation is favorable only for orientation. Oriented steel. Orientation is favorable for linear cores. For linear cores like transformer, but not for circular cores. But not for circular cores. All rotating machines, non-oriented steel. All rotating machines. Machines with a non-oriented steel. The non-oriented steel. Okay? Yeah. Because with orientation means in transformer, I think you are familiar about this. In transformer, if all the grains are oriented in a particular direction, if the flux is passing, all they are oriented on diagonal direction, then it will be, yeah, magnetic properties are improved. But whereas in circular case, circular core, in which direction the grains will be oriented, tell me? And everywhere the direction of rotation will changes. The direction of rotation changes, na? Yes. You cannot orient in a particular direction. Instant to instant, there are going to be changes. It's not favorable. No use of it. Orientation, it won't work for cylindrical machines. Circular cores, only linear cores. That's the reason all rotating machines made with non-oriented steel. Of course, silicon will be added everywhere. Nowadays, silicon steel with silicon. What is the advantage of silicon? With the addition of silicon, resistivity of the magnetic material increases. With the addition of silicon, the resistivity of the magnetic material. The resistivity of the magnetic material increases.
ఫిష్ కూడా అంటే ఫిష్ కూడా చాలా మంచిది అసలు దానికి. ఫిష్ కూడా
Resistivity of the
మంచిది.
magnetic material is. Resistivity of the magnetic material increases. Increases. So that eddy current losses will reduce. Na? Yes. So that eddy current losses will reduce. Eddy current losses will reduce. Okay. Normally silicon is added 4%, 5%, up to 6% silicon addition is common. But with more content of silicon, if you add more silicon, what will happen? Material becomes brittle. With more concentration of silicon, material becomes brittle. Mechanical strength will reduce. With more addition of silicon, 6%, 3% enough. With more addition of silicon, the material becomes brittle. Material becomes brittle. Material becomes brittle. Yeah. Anyhow, fine. Anyhow, lamination is standard process. With the lamination, again eddy current losses will reduce. But in addition to lamination, silicon content is also will reduce the eddy current losses. By adding silicon, resistivity of the magnetic material increases. Okay. Coming to in alternator, type of slots, open slots are preferred. In alternator, open slots are preferred. Open slots are preferred. Right? But the induction motor semi-closed slots are preferred. And you may be knowing there are three types of slots: na? Closed slots, semi-closed slots, open slots. But alternator, open slots are preferred. Open slots. Why? Because for easy access of winding, more opening means placement of the winding or placement of the insulation. It is easy. Large rating of alternator. No? Yeah. But power factor can be controlled. Power factor, all those things is not a problem. Open slots are preferred. So for example, this is the one particular slot I can take. This is one slot, say. One slot, completely open slot. Slot, na? Yes, it's a slot. Stator core, we are doing one slot. Like this. I'm showing the open slot. First, we will keep insulation. Na? Insulation is compulsory. Insulation, where it is insulation between the winding and core, is the insulating material. Insulating material is kept first. Inside of that, conductors are placed. Armature conductors. There are multi-turn coils. The armature winding can be kept in this. Insulating material. This is insulating material. Red color is insulating material. Insulation. And inside that is winding. This is the winding. Okay. This is the winding. Conductors. Conductors. Now winding slots are opened, na? It may fall down. Winding may fall down. Who will give the support for that? Who will give the support? Slot wedges. They are called slot wedges. Slot wedges means they are like this. Slot wedges, these are said to be slot wedges. They are made with, they are also made with steel plates. Steel plates. This is called having some thickness. They will have some thickness. These are said to be slot wedges. Slot wedges. Slot wedges. Made with steel. Steel plates. Steel plates in the form of plates. Plates. And this will be kept here. The same will be kept here so that winding cannot fall down. Winding cannot fall down. Winding cannot fall down. Exactly, it will be fit here. These are said to be slot wedge. We are keeping the slot wedge here. This is the slot wedge. Slot wedges. So that slot wedge, what it will do? It will give the support for the winding. It will give the support for the total armature winding. Though slot is open, winding cannot fall down. It will give the support for that. Yeah, this is the stator. Here I am showing only one slot. Just I am showing only one slot. Like all other slots also like this. Okay. This is the stator construction. Now come to the rotor construction. Rotor, based on the rotor, there are types of rotors, no? Salient pole rotor and cylindrical rotor. So let us see first salient pole rotor. Salient pole rotor. You have taken this now? Next, I am going to the next page. Yeah. Salient pole rotor alternator. Salient pole rotor alternator. Salient pole rotor alternator. Salient means projected type of rotors, projected poles. This is the stator. First I am drawing the stator. Okay. This is stator. Front view I am taking, front view. And rotor will be rotor. The poles can be fixed on the shaft. This is shaft shape. This is one pole. Salient pole, projected nature. One pole. Another pole. There are 4 pole. I am taking 4 pole machine. We are going to see very important conclusions. 4 pole. Okay. This is stator. Stator is like this. The rotor poles also you can extend like this. The rotor poles. are the salient poles. Okay, yeah. Yes. Projected nature on this field winding can be kept. Outside is stator and this is rotor on that field winding. So this is a field winding. And again, field winding is kept on the pole core. They are excited with DC. Excited with DC. Okay, yeah. This is the salient poles, salient pole rotor. Salient pole rotor. Based on this current direction, see this act as a north pole, say this will be south pole, this is north pole, south pole. They must be adjacent poles. Adjacent poles must be alternating. So north, south, south. I am drawing winding properly only on first slot. I am drawing only winding on first pole. Others blindly I am drawing. Okay, actually how this is the pole corner, winding can be kept like this. And second pole, south pole also winding can be kept on the pole core. This is pole core, rectangular piece is there, that is a pole core. This entire thing pole core. This is the pole shoe. The top portion is pole shoe. So winding is kept on the pole core. Winding is kept on the pole core. Here also pole core. Here also pole core. But here I am just drawing blindly. Blindly I am drawing like that. Okay. And you know that before, every time we are coming across the poles, instead of explaining every time, you tell me, I will draw here how it is act like. See here. This is one pole. No? And this is another pole. On this, I am keeping the winding like this. Winding. On this, winding can be kept like this. Okay. Fine. Yeah. This is plus minus. This is also plus minus. Can you tell me what is the polarity of the pole? First one. How first one is acting as north pole or south pole? Two poles I am taking. First one act as a north or south pole. This is the current direction. Based on the current direction, this act as north pole. It is giving the flux outwards, na? Yes. Which is giving flux outwards, it is north pole. Apply thumb rule. Current is entering, leaving. It is giving the flux. So it acts as a north pole. Second one is current is entering that side, leaving. It is sense of the winding is different. First one, sense of the winding clockwise. You are started this side. Once you are started this side means, for example, this is a core, say. This is a core. We are started this side. So therefore you need to continue like this, clockwise. But bottom one, you started that side, opposite side, wound in counterclockwise. Counterclockwise. But even both are plus minus polarities are same, but current direction is reversed. Na? First one acting as a north pole, next one is acting as a south pole, because it is receive the flux, south pole. Okay. The polarity of the pole is depends upon what? Two things. Polarity of the pole depends on the two things. One is sense of the winding, another one is direction of the current. Direction of the current. So first one, the wind was wound in clockwise direction. Bottom one is counterclockwise direction. Though both are with the same polarities, current direction is reversed automatically. Current direction also depends on the sense of the winding. Na? Yes. Okay. But don't think. First one, it is acting like a north pole. If I want to act as a south pole, what to do? Tell me. The first one, it is acting like a north pole. I want to make it as a south pole. How you can do it? Just interchange the current direction. Interchange the current direction or interchange the terminals. Current direction changes. But in practical generator, all they will be wound in the same direction. Only thing is north pole, adjacent south pole. Their interconnection will be so that to form the opposite poles. If this is acting as a south pole, what I will do? Just interchange the beginning ending, north becomes south. Okay. Yeah. These are the salient poles. Salient means projecting nature. Projecting, coming out. One pole and this another pole, projecting nature. Like just like a projection coming out. At the cylindrical rotor, it is not like cylindrical is totally circular shape. Okay. Important observation is, see, this is called direct axis. This is called polar axis or direct axis. Polar axis. Or it is called direct axis. And this is interpolar axis. This is also another interpolar axis. Interpolar axis. It is called Q axis, quadrature axis. And this is also Q axis, quadrature axis. Along the direct axis, air gap is minimum. Along direct axis, air gap is minimum. Quadrature axis, air gap is maximum. See, gap is nothing but air gap is the gap between stator and rotor. Gap between stator and rotor. Air gap is minimum here, minimum. But whereas here maximum, air gap is maximum. Are you finding? I'm showing with highlighter. Air gap is maximum here. Air gap is maximum along quadrature axis, but air gap is minimum along the direct axis. Direct axis. Air gap is non-uniform. So the conclusion is air gap is non-uniform. Air gap is non-uniform. Air gap is non-uniform. Non-uniform. But that is minimum along direct axis. Minimum along direct axis. Air gap is minimum along direct axis. Maximum along quadrature axis. Maximum along quadrature axis. Air gap is maximum along the quadrature axis. Because along the direct axis poles are there, then gap is covered by the pole. But quadrature axis there is no pole. So air gap is created. Air gap is created. Air gap is non-uniform. But even air gap is not same even under the pole shoe. Dear students, see, even here also air gap is not constant under the pole. It is changing, na? This air gap is changing. Air gap is more. Air gap is not same. It is also different. Right? It's different. See, air gap is more here. decreases here, decreases here. Air gap is minimum, air gap is more. Even under the poles view also air gap is not same. Purposely it has been done. Purposely for making the flux distribution sine wave. Let me show that. The meaning of this is air gap. This is a pole, say, stator pole. If you want, you can design your pole like this, but this is not preferred. This is not preferred. Purposely, we are doing like this. Purposely, the core of the rotor is like this. Purposely, we are designing. I hope you are getting difference between these two. First one, air gap is uniform. Second one is air gap is non-uniform, minimum along direct axis. Reason why we are doing, because flux is equal to MMF by reluctance. Na? Yes, flux is equal to MMF by reluctance. And that is proportional to air gap length. Flux is proportional to air gap. So, in the first one, if you take here under one pole, if you draw the flux distribution, B wave, flux is more means flux density also more, na? Yes. B wave, see here, gap is more here. Gap is more means when air gap is more, flux is less. Air gap is more, flux is less. Coming to here, air gap decreases, flux increases. Flux increases, air gap decreases, flux increases. But from here to here, air gap is constant. Air gap is constant. Air gap constant. That's the reason flux will be constant. Flux is going to be constant from here to here, it will become constant. Whereas from here onwards, again, air gap is increasing. When air gap increases, flux will reduce. So therefore, the flux distribution is a flat topped wave. If you draw that, flux distribution is going to be flat topped wave. Flux distribution flat top. This is under North Pole. Similarly, under the South Pole, it is going to be like this. Similarly, South Pole, it will be like this. So flux distribution is flat top. When flux distribution is flat top, then generated EMF also flat top. Is consisting of all harmonics. It is said to be consisting of harmonics. We do not prefer this type of waveform. No. We want flux distribution sinusoidal. Because main reason for the production of harmonics is non-sinusoidal flux distribution. The main reason, non-sinusoidal flux distribution. This is the main reason, flat topped wave. But we want to design our pole. We want to design our pole for the production of the sinusoidal flux. I don't want flat. First of all, can you get me why flat we are getting? Because air gap is constant. Air gap is constant. Under the pole shoe air gap constant, that's the reason we are getting flux constant. Okay. But for making sinusoidal, it should not be air gap under the pole shoe, not same. So what to do is, see, what we have to do is, again under this, under one pole pitch. Under one pole pitch. So here air gap is maximum. Here air gap is maximum. Flux is minimum. Air gap decreases. Flux increases. Air gap decreases. Air gap decreases. Air gap decreases. Air gap is minimum only here. Minimum only here means flux will be maximum at the center of the pole. Again air gap increases. Air gap increases. Flux decreases. Air gap increases. And continuously air gap changing. Flux distribution is a sine wave. It is a flux distribution is a sinusoidal waveform. Similarly, under the south pole also. Under the south pole also flux distribution. This is under north pole, south pole. So this is the flux density wave and induced EMF. Is a sinusoidal. Sinusoidal. Particularly, we prefer this. What is x-axis? Space with respect to space. That is with respect to space. Or with respect to air gap periphery. In other words, it is with respect to air gap periphery. Air gap periphery or with respect to space, it is called space. Respect to air gap periphery or with respect to space, flux distribution must be sinusoidal. This is preferred. This type of waveform is preferred. This is preferred. Okay, this is what we want. It is preferred. So, the main reason for the production of harmonics is non-sinusoidal flux distribution, like first one. But flux distribution must be sinusoidal. In salient pole machine, flux distribution can be made sinusoidal by chamfering the salient pole. This type of pole is called chamfered salient pole. This pole is said to be chamfered salient pole. The minimum air gap along the pole center and the air gap is increases towards the pole ends. Correct? Air gap is increasing towards the pole ends. That is said to be chamfered salient pole. Chamfering. So conclusion is here. The main reason for the production of harmonics is non-sinusoidal flux distribution. Is non-sinusoidal flux distribution. The flux density wave. Non-sinusoidal flux distribution in the air gap. In the air gap. Right? Like in diagram 1, in figure 1. This is figure 1, say. In figure 1. First figure, figure 1. In salient pole machine, flux distribution can be made sinusoidal by designing the salient pole. By designing the salient pole such that having minimum air gap along the pole center, increasing towards the pole ends. Increasing towards the pole ends. So, yeah, in salient pole machine, flux distribution can be made sinusoidal by designing the salient pole. By designing the salient pole such that having minimum air gap along the pole center, minimum air gap along the pole center, and increasing towards the pole ends. Increasing towards pole ends. Towards pole ends. Right? This is said to be chamfered salient pole. This is said to be chamfering. Chamfered salient pole. Chamfered salient pole. By chamfering, flux distribution can be made sinusoidal. Minimum air gap along the center means flux becomes sinusoidal. Okay. Yeah. The chamfering is proportional to sin theta. That is also one question. Air gap length under the pole shoe is proportional to sin theta or proportional to cos theta. First, let me give the conclusion. The air gap length. The air gap length under the pole shoe. Air gap length under the pole shoe is proportional to sin theta or inversely proportional to cos theta. Proportional to sin theta, inversely proportional to cos theta. Where theta is in electrical degrees. Theta is in electrical degrees measured from pole center. Measured from pole center. Theta in electrical degrees measured from pole center. Proportional to sin theta, inversely proportional to cos theta. In other words, let me explain with the pole. This is our pole, say. Right. The air gap. Straight or pole. Right? Yeah. Now theta. Yes. Okay. The pole air gap, the center of the pole, na? Yes. This is theta is equal to 0 here, says some theta is equal to 60 degrees. This is theta increasing, increasing theta. Okay. So sin 0 air gap is minimum, na? Yes. If you take here, gap is minimum, but here gap is maximum. Gap is minimum here, gap is increases. As theta increases, sin theta increases, gap also increases. Sin theta increases, gap also increases, right? So if you do exactly proportional to sin theta, inversely proportional to cos theta, then you will get generated EMF is more sinusoidal and it will be flux distribution is sinusoidal. Flux distribution will be sinusoidal. Okay. Yeah. Now, this is itself objective question. Air gap length under the pole shoe. Sin theta proportional to cos theta. Okay. Yeah. Next point. Yeah. See. Salient poles are projecting nature. Salient poles are projecting nature, coming out. One pole is like this, another pole projecting nature, coming out. Cylindrical, smooth cylindrical. They won't, pole do not come outside of the rotor periphery. A part of the rotor will form as a pole. But whereas the poles are fixed to the shaft, projecting nature. And winding is concentrated winding. Winding is kept on that. The salient pole rotor is not mechanically balanced well. It is not mechanically balanced well. So if these rotors are driven at high speeds, large centrifugal forces will develop. If you rotate rotor at high speeds, centrifugal forces, vibrations are more because air gap also non-uniform, more air frictional losses, large centrifugal forces. the rotor will damage. Rotor will damage. So these type of rotors has to be driven only at low speeds. That's the reason these are called low speed alternators. Low speed alternators. Low speed alternators. Let me write the conclusions. Okay. See, if the rotor is driven, yeah, due to salient poles, come a projecting nature, the salient pole, due to salient pole projecting nature, the rotor is not mechanically balanced well. Rotor is not mechanically balanced well. Mechanically balanced well. If these rotors are driven at high speeds, high speed, large centrifugal forces takes place. Large centrifugal forces takes place. Then the rotor cannot withstand. The rotor cannot withstand this. Rotor cannot withstand these centrifugal forces. Rotor cannot withstand. Therefore, these rotors has to be driven only at low speeds. Therefore, these rotors to be driven at low speeds. That's the reason called low speed alternators. These alternators are low speed alternators. High speed rotor cannot withstand. That's the reason these alternators are called low speed alternators. Alternators are called low speed alternators. Low speed. Then it's speed range. How much speed it has to be driven means speed range. Speed range is 50 RPM to 1000 RPM. 50 to 1000. 50 minimum. 1000 is highest speed. 1000 is maximum. Highest. But more common is 200 RPM to 400 RPM is more common. Commonly, salient pole alternators are used 2 to 400 RPM. 200 RPM, 250 RPM, 300 RPM, that is more common. 2 to 400 RPM, low speed. But whereas if you take a cylindrical alternator, it will be 3000 RPM. 3000, this is 300, say that is 10 times 300 RPM, 3600 RPM. High speed, these are low speed. 50, minimum 50,000 maximum. Then when low speed means, if you want for 50 Hz frequency, number of Wow. I think I might have lost. Okay. Dear students, just there was a problem with the internet, so I lost. Yeah, fine. So we are going to close quickly. We're going to close quickly. Yes. So the thing is, number of poles for 50 Hz frequency, the speed range is, what is that? Speed range is 50 RPM to 1000 RPM. Low speed only. 200 to 400 is more common now? Yes. More common. But for 50 Hz frequency, we want 50 Hz frequency. For frequency is equal to 50 Hz, number of poles. Number of poles are 50 means 120, 1000 means 6. 6. Because F is equal to Pn by 120 or N is equal to 120 into F by P. N is equal to 120 into F by P. So poles are inversely, speed is inversely proportional to poles. Inversely proportional to poles. Okay. Our poles are inversely proportional to speed. If you want to write poles, say this is N. Poles are inversely proportional to speed. Low speed, 50 RPM means 120 poles are required. 120 means very large number of poles. Large number of poles. So it will have larger diameter. Since more number of poles, therefore larger will be the diameter. Larger will be the dia of rotor. Larger will be the dia of rotor. Okay. But when diameter is larger, length must be smaller. Length must be smaller. Because power is proportional to volume of rotor. Power is proportional to volume of rotor. The power is proportional to d square L. The pi d square, na? Pi d square L. Volume is nothing but volume is equal to how much? Pi d square L. So power is proportional to d square L, where d is the dia of rotor, where d is the dia of rotor, L is the axial length. Axial length of rotor. Power for any rotating machine, power is proportional to volume of the rotor. Large volume means more tons, more number of tons you can accommodate. Correct? Yes. Larger diameter. So power is proportional to volume of the rotor. But when diameter is larger means for a given power, when dia is larger, length must be reduced. Length must be smaller for a given power. See. The statement is salient pole alternator will have salient pole alternator will have larger diameter, from a smaller axial length. Smaller axial length for a given power. For a given power or a rating. For a given power or given rating. For a given power or given rating, salient pole alternator will have larger diameter, larger dia, smaller axial length. for constant power. For constant power. See, diameter. I will come to the reason why. For constant power, why it is proportional to volume, I am going to explain that point. First, diameter. Diameter is nearly 5 times that of the length. 5 times that of the length. See, L by D ratio. L by D ratio is 1 by 5. 1 by 5. That is nearly 0.2. 0.2. You can identify by looking physically. Looking physically, it is a salient or cylindrical means. If it is having larger diameter, smaller length is smaller, diameter is larger. Then I can say it will be the salient pole alternator. Salient pole alternator. Okay. Let me explain why your doubt may be it is having larger diameter, why length has to be reduced. Length has to be reduced. Let us see. Reason is when dia is larger, when diameter is larger, say stator dia also larger, na? Yes. When rotor dia is larger, stator dia also larger. Stator dia also larger. Rotor dia larger, stator dia larger, so that more number of slots can be accommodated. Na? Yes, more number of slots can be accommodated. More number of turns can be accommodated. Then they need not to be lengthy turns are not required. Lengthy turns are not required. Shorter length is enough. Shorter length is enough for a given voltage, for a given power. This is itself question. This is one particular slot. If you take particular slot, in this we are keeping conductor, na? Yes, conductors we are keeping. So more number of slots can be more. Length is less for a given voltage, for a given power. Why? Because E is proportional to L, na? Length of the conductor. E is equal to BLV sin theta. The E is proportional to L. L, active length of the conductor. Active length of the conductor. But E also equal to 4.44 Kp Kd phi ft. That also we are going to see. EMF equation of alternator. 4.44 Kp Kd phi ft. The E is proportional to number of turns. T is the number of turns. Therefore, E is proportional to length and number of turns. Length. This is length. Length of conductor or turn. Or turn. But whereas this T is number of turns. Number of turns. So induced EMF is proportional to both number of turns and length of the turn. Turns are more, EMF is more. If number of turns also, both are turns only, number wise, length wise. But I want constant voltage. Power is proportional to voltage. Power is proportional to voltage. Assume power is constant. Power is assumed constant. Therefore, voltage also must be constant. Therefore, when E proportional L into T means as number of turns are more, then length must be reduced. Length must be reduced for a given voltage, for a constant voltage. So with larger dia of rotor, stator dia also larger, more number of slots can be accommodated, more number of turns can be accommodated. Then they need not to be lengthy. They need not to be lengthy. Lengthy turns are not required. Shorter length is enough. Shorter length is enough. So the statement is with larger dia of rotor. With larger dia of rotor, stator dia also larger. Stator dia also larger. So that more number of slots can be accommodated. More number of slots can be accommodated. More number of slots can be accommodated. More number of tons can be accommodated. More number of tons can be accommodated. More number of tons can be accommodated. Then they need not to be lengthy. Length avasara ledu. Then they need not to be lengthy. Need not to be lengthy. Right? Shorter length is enough. They need not to be lengthy. Short length is enough. Correct? Yes. This is the reason. They need not to be lengthy. Shorter length is enough. For a given voltage. For a given voltage. For a given voltage. For a given voltage. Okay. I hope this is very, very clear. Nothing is there. If diameter is larger, stator dia also larger, space is more. So more number of slots, more number of tons. And more number of tons, they need not to be lengthy tons. Shorter length is enough. For a voltage, for a fixed voltage, for a fixed power. And you may raise a doubt. No, sir, diameter is larger, length also larger means when diameter is larger, more tons are there, and length also more means EMF is more. EMF is more, power is more, size of the machine also more, cost also more. But what is your requirement? For example, you want 200 kVA alternator. 200 kVA alternator means you have to design 200 kVA alternator only. 200 kVA alternator only. If salient pole means definitely diameter is larger, length you have to reduce. Otherwise, length also larger means diameter is already larger, length also larger, more generated MF, more power output, more kVA rating. You are getting 400 kVA alternator, but he has asked only 200. What is the use of that? 400 kVA alternator, my requirement 200 kVA. I need to operate only half rated. Efficiency is less. All this comparison is based on the constant voltage, constant power. For a given power, right? Yes, for a given power. Yeah. And these alternates are going to be used in hydropower station. Suitable prime movers for these alternators are the low speed turbines. Low speed turbines. The speed is low. When speed is low means low speed. Turbine also must be low speed. Suitable turbines are suitable turbines. Suitable turbines are prime movers. Prime movers. They are the hydro power plants. Hydro turbines. Hydro turbines means water turbines. No, water turbines. Water turbines. Hydraulic turbines. Water turbines. That is, they are, for example, Pelton wheel. Pelton wheel. Okay. Pelton wheel. Francis. Right? Etc. Kaplan, Francis, Pelton wheel, Kaplan, turbine, Francis, etc. Hydro turbines. They will be low speed turbines. Water turbines are low speed. Na? Water driven turbines are low speed. And diesel engines also. Diesel engines. Diesel engines. Diesel engines also low speed. Hydro turbines also low speed. Therefore, salient pole alternates are used in hydroelectric power stations. They are suitable. Salient pole alternators are suitable for hydroelectric power stations. Hydroelectric power station. Hydroelectric power stations and diesel power stations. Diesel power stations also. Diesel power stations. Diesel power. Hydro and diesel. Hydro power stations and diesel power stations. Hydro and diesel. That's the reason they are sometimes called as hydro alternators. Salient pole alternators are also called hydro alternators. Since used in hydro power stations, salient pole alternators are called hydro alternators. Hydro alternators. Since used in hydro power stations, used in hydro power stations. Okay. And sometimes they are also called a engine driven alternator. Engine driven alternator. Engine driven alternator. Because diesel engine is used as prime mover. Diesel engine as prime mover. Okay. So you should be aware about the terminology. Terminology, it can be called as salient pole alternator, low speed alternator, hydro alternator, engine driven alternator. All meanings are same. So you should have idea about all these things. Fine. The last part is a damper winding. Of course, that we are going to see. Damper winding. Tomorrow we will see damper winding. Damper winding. Last part of that, damper winding. Damper winding is used to eliminate the hunting. Eliminate hunting. Damper windings are placed under the rotor core. It's used to eliminate the hunting. Hunting under rotor oscillations. Okay, that we are going to see tomorrow. So it is almost 9:15. So I will stop here and we will continue tomorrow. Okay. Yeah. And tomorrow your class is, I think you might have got already information. Tomorrow class is from 7 a.m. onwards. 7 a.m. onwards. Up to it may be 1 o'clock. Or let us see time. Is it 1 or 12 or 12:30? We will see. 7 a.m. onwards. 7 to 1 roughly. Schedule is 7 to 1. But whether we continue up to 1 or beyond 1, we will decide. Okay. Tomorrow. Yeah. Now you are raising doubts. Let us attempt your doubts. Yeah. And those who are not having doubts, you please leave. Otherwise, you can stay here. Okay. Yeah. So who is raising? Raise your hands. Nitesh Kumara. I'm unmuting. Please, you can ask. Or you yourself, you can unmute. What are your doubts? Hello?
Hello, sir.
Yeah, hello. Tell me.
Sir, I have a doubt regarding this. Just now, what you explained about how, why we are reducing L, sir. Could you explain this once more, sir, to make the bar?
More means, see, always you need to compare with respect to what? You need to compare with respect to power. Power is proportional to volume. D square L na? Yes.
Yes.
I want constant power. Power is constant, say. For a given power, that's the reason I have written. When diameter is larger, say. When diameter is larger, length also larger, na?
Yes,
Rotor
sir.
dia is larger, stator dia also larger.
Yes, sir.
When diameter is larger means more slots, space is increased. You
Yes,
can
sir.
accommodate more slots.
Yes, sir.
When more slots means more tons.
Yes, sir.
When tons is more, E proportional to L into T, na?
Yes,
When
sir.
tons is more means they need not to be lengthy. Shorter length of the tons are sufficient
Yes, sir.
for a given voltage because power is proportional to E. E
Okay,
should be
sir.
constant, E constant for a given power. So that's the reason when definitely number of tons will increase. Reason is larger diameter, space is more. I need to keep all the tons, na? All the slots. We cannot keep empty slots, all the slots.
Yes, sir.
More tons.
Yes, sir.
And then the winding tons need not to be lengthy. Shorter length is enough because tons already we have increased. Length will be smaller for a given voltage, for a given power. Okay.
Okay, sir.
Otherwise, you are also increasing the length means voltage. There is no limiter. You can go up to infinite alternator also. But infinite alternator, what you will do? Your requirement is for a given power. That's what for a given power. You want 100 kVA alternator. Say for example, you need to design 100 kVA alternator only. If you are going for salient pole, definitely rotor will increase.
Yes, sir.
Rotor is more poles. Rotor will increase. Diameter. Length must be smaller.
Okay, sir.
Ah.
Sir, so like rather than like instead of like again from this equation E is proportional to LT, what if we increase the length and decrease the number of turns, sir? Then also power is constant, no?
Yeah, but salient pole alternator diameter must be larger, na? More poles you are keeping. Salient pole, hydro turbines are low speed, they will rotate.
Okay,
Hydro
sir.
200, 300, that much only. So therefore,
No.
you need to go for example, 200 RPM, 30 poles. If you keep all 30 poles on the rotor, diameter will definitely more.
Oh, yes, sir. Effective diameter will be more.
More. Then stator dia also more, na? D definitely more. That you
Okay.
cannot reduce. D is more definitely. Therefore, more slots will come automatically. More tons will come. Then need not to be increase the length.
So that time will rather than that time will compensate it by reducing the length of the machine.
Yes. For a rated voltage, if you want rated voltage, length can be reduced. Otherwise, length also more means EMF is more. Rating also more. When rating is more means size is more. Cost of the machine also more. But your requirement is you are asking for 100 kVA. The person is designing for 200 kVA. What is the use of this? Your requirement 100 kVA. 200 kVA means you need to operate half load condition. Efficiency is less. Your machine must be for a given power. That's the reason I have written for a given power. Any statement is valid for a given power, given voltage. Brother, cylindrical alternator. Next we are going to see tomorrow cylindrical. It is high speed. High speed means minimum poles, 2 poles. 2 poles means stator diameter is smaller. When diameter is smaller, number of slots also less.
Yes.
Number of tons less. But then I can increase the length. So that I will get there also same voltage. For example, here I am getting 10 kilovolts for salient pole. Cylindrical also I want 10 kilovolts means this will have larger diameter, that will have larger length.
Okay, sir.
Yes.
Sir, and one more thing regarding the salient for rotor construction, the diagram could you take, sir? The diagram, the diagram.
I think the diagram I lost actually in between.
Due to the network issue, sir.
Network issue. That class. Okay, you tell me, I can understand what is your problem.
Sir, in that the poles that we wrote were like north, then after 90 degrees south, then again 90 degree north, and then again 90 degrees south.
Yes.
So my doubt is like usually when I see many books I've seen this, why don't they go for like north and then exactly 180 degree opposite south, then north and south?
Just a minute. Tell me. This is 4-pole machine. You want 4-pole?
Yes, sir.
Okay, 4-pole machine is there. This will be north pole.
Then the what I'm saying is if the top one is north pole, then the diametrically opposite one, why can't we can make it a south pole and then the other one north?
You mean to say this is also, you want to say it is South Pole?
Yes, sir.
Okay.
Then the other,
See. Then what is this pole? You want to say south? This is south?
north, sir.
Just a minute. You want to make this is a north.
Yes,
This is south.
south.
Then how the flux will passes? What is the path for the flux? Path for the flux. This cannot exist like this machine. For example, 4-pole machine is there, say,
Yes, sir.
whatever I have drawn, 4-pole machine means flux per path, north pole, this is south pole, north pole, south pole. This is a north, south, north, south. How flux path will be? Path will be this north pole to south pole. It will come like this, return path. North pole to south pole, return path. Okay. And this north pole is there, na? Here 5/2 will come to the south pole, 5/2 come to the adjacent south pole. Similarly, from this north pole, 5/2 will come to here, 5/2 will come to here. Okay.
Sir, but in that case, in the left one, there will be only 2 loops. That's all, no, sir. That's the only difference.
No. This is clear, na? This diagram.
Yes, sir.
Now tell me here how it will go. This north pole to where it should go? South pole.
Yes, sir.
Where is another path? It will not go to the next north pole.
No.
It will not exist. Is it practically machine will exist like that?
No, it will form an non-uniform flux.
Non-uniform. We cannot get only this side. This side is not going means what is the meaning of that? Pole never exists like that.
Okay, sir.
Rather than what you can say, this north pole, these together can be considered as a single pole only. This both can be, I can treat it like a north pole only.
Yes, sir.
This becomes 2-pole machine. And physically it is you are feeling like a 4 poles, but these 2 will act like a north poles only together.
Okay, sir.
So
okay, so this will do. So if you change the windings such that this is north pole, and this one is south and south, you can make a 4-pole into 2-pole.
2 poles means but in between there is a gap is there. Actually, okay, theoretically you are feeling, but practically is it fine? Can be accepted? It cannot be accepted.
Okay.
Why we will go unnecessarily? Of course, it is only just our theoretical discussion, but practically never be like this.
Okay, sir.
Never be like this. Non-uniform. You cannot get a flux distribution under each pole is not same. And that to be okay. North pole flux is going. Where this another pole, it cannot go like this.
It can't, sir. That's what my doubts are. Why it can't go from that north pole to this diametrically opposite south pole from the top?
See, this is going. No, total flux is going like this. Total flux is going like this. This is your point. North pole to south pole. Okay, like this. Right?
Yes, sir.
This is coming like this, and here it is coming like this.
Yes, sir.
Right? Yeah. And it is total 5 will be going to only the south pole.
Yes, sir.
5 is only going to the south pole.
Yes, sir.
Okay. From this,
is it not possible to go to this south pole, this diametrically opposite south pole, through that core?
Whatever I have given, this north pole to south pole only will come flux. This
Yes,
north pole to this north pole, it cannot come.
It can come to the south pole.
This south pole,
from the top north pole to this bottom south pole, it can come, sir.
You mean like this, sir?
Yes, sir. Exactly, sir.
It will not go because what is the length of this?
Reluctance will be more.
Reluctance is more and the length is more.
Sir, in this case only, also, if you go for something like this oriented CRGO, then in that case reluctance will be comparatively reduced.
Okay. You see, this is north pole. It is coming like this. This north pole also it is coming like this. And what is the flux under this pole? See, yeah, your point of view. This flux is coming like this. This flux is going at a total 5. 5 divided 5/2 coming to here, 5/2 coming to here. Okay. and this north pole to this phi is 5/2 will come to here, and you are also expecting this another 5/2 coming like this.
Yes, sir.
Do you think both 5/2 coming, right? Is this length is not same, no?
No,
Length
sir.
is not same. Definitely this 5/2 is not equal to this 5/2.
So the distribution will change.
Distribution little changes.
Yes,
Okay.
sir. Yes, sir.
This is uneven. This is uneven.
Okay, sir.
Okay. You may be taking the path as you want. Yeah, it should be even.
Okay, sir.
Uh,
That's it, sir. Thank you, sir.
Okay. Right. Yeah. So any doubts are there? I'm going to close our session. Hello.
Good evening, sir.
Yeah. Tell me.
Sir, in the last topic, you have said that we are increasing the diameter, no, sir. So number of slots can be increased, no, sir.
Yes.
Sir, for a production of the voltage in that particular phase angle, the conductor should be placed in equal regular intervals, no, sir.
Yes. Yes.
Sir, but how, if even though the diameter is increasing, how can we place the conductor such that that angle is being constant, sir?
See, number of slots are increased means for each angle for each slot is going to be reduced. You can have an alternator with a three-phase. Alternator can be a three-phase, 4-pole, 24 slots can exist, or a three-phase, 4-pole, 48 slots also can exist. Won't it exist?
It can exist, sir.
It can exist. The number of slots are increased, angle for each slot reduced.
Okay, sir.
Angle for each slot reduced, but there will be even only. All slots will be equally displaced, no?
Okay, sir.
All slots are equally distributed. That is not a matter. You can have
Okay,
48 slots, 24 slots, any number of slots, but only thing is slots must be even number.
Are there should be multiples of 24, sir? Like that, for example, you said these are multiples.
Multiples of six. Because for each phase, at least three phase, no?
Yes, sir.
Three phase, how many minimum number of slots? 2. At least R dash, no?
Yes, sir.
So for example, 2-pole machine is there. 2-pole machine, if I want to keep R phase winding, this is R phase coil. Okay. Next Y phase coil also must be one there, na? Y phase coils and B phase. At least minimum 2. And how many slots? Slots must be multiples of 6. Slots for three-phase machine, multiples of 6. Because at least 3 into, for each phase at least 2 slots are required, na? R dash, Y dash. Now you can take multiples of 6 means what is that? 6 into 1, minimum 6 slots. 6 into 2, 12 slots.
And multiples of 6.
6 into 3, 18. 16 to 4, 24. 16 to 5, 30 slots also you can have. 16 to 6, 36. 42, 48, like that. Multiples of 6, you can have any number of slots.
Okay, sir. I got clarity, sir.
It is 6 only. You can verify any machine.
Yes.
Three-phase machine, number of slots must be multiples of 6.
Okay, sir. Thank you, sir.
Yeah. Okay.
Hello, sir.
Hello. Yeah, tell me, ma'am.
Sir, what is the meaning of traction torque, sir?
Sorry, traction?
Torque. You said no, sir, while explaining torque due to inertia and friction torque. While explaining.
Yes. Friction torque, inertia torque. Electromagnetic.
I got that one, sir. I didn't get the meaning of traction torque meanings.
Friction torque, frictional torque.
Frictional torque is also known as traction torque, sir.
No. I think instead of I, you will be feeling FRA. No, FRI. Please correct it. Frictional torque.
Okay, sir.
Not fractional, frictional torque. Friction, due to friction, it will come. Brush friction, bearing friction. Friction also opposes the rotation. Some extra torque is required to overcome that friction. Friction torque. Friction, not fraction. Please correct me.
Fraction. I am asking traction, sir. TRACTION. Fraction.
Friction torque won't no. That is not this is not same.
Okay.
No.
Okay, sir.
Friction
Sir, again.
only. No
Okay.
torsion. Torsion won't exist here. Friction only exists. Yeah.
Sir, again you said no, sir. TEM is not an advantage or disadvantage. It is just a principle. Can you
Yeah.
explain? How, sir? Can you explain?
It is a part of the principle, ma. Without electromagnetic torque, generator exists.
No,
No.
sir.
Electromagnetic torque proportional to current into flux. When current is proportional to load, load. This is the conductor, say. This is a conductor. Okay. No load condition, what is the current? 0.
0.
Torque also 0, no torque. But when load is connected, path is closed, it will drive the current. Your load connected, current is passing. As load increases, current also will increase, na?
Yes, sir.
Current increases, torque also increases.
Okay,
Therefore,
sir.
the torque only load torque.
Okay, sir.
Torque only load torque. That is itself power output. The torque into omega only power output. Electromagnetic torque only load torque, that's what I told. It is a power output. So it will exist. It is a part of the principle. Prime mover torque exists. Simultaneously, electromagnetic torque also exists. But both opposes. But which torque is more? Prime mover torque is more. Rotation is by the prime mover only. Torque keep on increases always. Torque is not there, say electromagnetic torque is not there. How much prime mover torque is required? Small is enough. You apply some 10%, it is rotating at synchronous speed. But when load is connected, what happened? Opposition will come. Then you need to increase your prime mover torque. As this is electromagnetic, load increases, electromagnetic torque increases, your prime mover torque has to be increased. So that TPM minus TEM must be balanced. Then machine rotated synchronous speed.
Okay.
So without TEM, there is no opposition, there is no power conversion at all. TEM is not there, means what is that? No load. Load is not there, means where the power conversion takes place. Who will take the power? Load has to be connected. When load connected, current will come, torque will come. Prime mover torque also exists. All they do exist in the machine. We are just knowing the importance of the TEM. That's all.
Okay, sir.
Huh?
Okay, sir. Sir, again in yesterday class you said, no, sir. Winding is spatially balanced, then the EMF will be physically balanced. You said one point, no, sir. What is the meaning of physically
Not
balanced?
Facially, not facially. Phase. PHA. Facially.
Facially?
Phase means 120 degrees.
Yes, sir.
Phase and space means periphery. R phase to Y phase winding 120 degrees. Phase. Periphery. State or periphery. Phase means angle. Phase, electrical angle. Phase angle.
Okay, sir.
This is said to be phase angle. They will have a phase angle is equal to 120 degrees. If you keep finding R to Y 120, Y to B 120, then you will generate the EMFs exactly 120 degrees phase difference. Like a 3-phase waveform, you will get it. Okay?
Thank you, sir. Okay, sir. Understood.
Right.
Thank you, sir.
Yeah. Hi. Anybody?
Sir, how can we increase the prime mover torque, sir, without changing the speed?
No. Prime mover torque to increase, you have to increase the steam input or water input. You have to open the valve.
But the speed will increase, no, sir, for rotated turbine. Speed of the turbine may increase, no, sir, if we increase the
Yeah.
steam.
Yes. Then why you will increase? If load is increased, then only I will increase the prime mover input. To maintain
Okay,
the
sir.
speed, when load increased, speed reduces. But to maintain the same speed, I will increase the
We
prime
are
mover
increasing
input.
the steam. Okay,
Yeah.
sir. Okay, sir.
That is
Got
only
it.
normally we will do.
With increase of the load, that electromagnetic torque is increasing. So that prime mover torque is decreasing. Again, we are increasing the torque with input of steam input.
Yes.
I got it.
Without that, if load is constant, unnecessarily you are increasing, means rotor accelerate definitely.
Yes, sir. Then that it will lose its synchronism, no, sir.
Exactly. Yes. Both must
Yes,
be
sir.
balanced. Both must. There
Yes,
will be
sir.
closed loop control system. Closed loop control system. Governor control system. When load increases, automatically it is more opening of the governor action will comes into picture. It will open. It will release the more steam or more water to maintain the speed.
Yes, sir. Yes.
In short duration, it can done all the things simultaneously. When increases, it will also comes into action. And if load increases, this will increase automatically. Speed will be maintained constant.
Okay, sir.
Okay. Right.
Sir, if mechanical torque is equal to sum of frictional torque plus electromagnetic torque, then how the net torque, then if net torque is 0, then how will the rotor rotate?
Net torque means, good question. This equation, see, yeah, very good. Prime mover torque is equal to J into d omega by dt plus B into omega plus TEM. Okay. Yeah. See, when this friction torque exists, while rotating only this equation exists. Yes, student. When rotating only this friction exists.
Yes, sir.
This equation valid only under running condition only it is valid.
Yes, sir.
Not zero speed. Zero speed it won't exist.
Okay, sir.
Equation. Omega is there now. When rotor is rotating, then only friction takes place. No?
Yes, sir.
When rotating, then only friction takes place. To overcome that, some of the prime mover torque is required.
Yes, sir.
This equation valid only under running condition. When omega is there, then only friction exists.
So, sir, when it is running, then the prime mover torque is equal to sum of all these torques. So, net torque is 0 or not on the prime mover?
Right?
On the rotor, sorry, on the rotor.
Net torque is not 0. See, prime mover torque is equal to, I will take under no load condition for easy understanding purpose. See, under no load condition, let me make it clear for you. Okay. Yeah. Load is not there. Open circuited. Prime mover torque. This is generator. Already it is running, say. When prime mover torque is given, forget about friction, inertia torque. Prime mover torque I have given. Tell me, when prime mover torque is given, electromagnetic torque 0, TEM 0. When I am given prime mover torque, will it rotate or not?
Yes, sir.
Will it rotate? Yes. When it is rotating, friction will come or not?
Yes, sir, it will come.
TI. Equation is balanced or not?
Yes, sir.
Do you think net torque is 0, therefore it won't rotate? Not like that. When you have given prime mover torque, then only it is rotating, then only friction is coming.
Yes,
then only
sir.
equation is valid.
Okay, sir.
Sorry, this is TB, na? TB. TB
Yes,
is
sir,
equal to
TB.
V into omega. Okay? For example, this is there. See, this is my rotor. See, hand friction between my bottle and the rotor, say, rotor and my hand. Fine.
Yes, sir.
When I am applying the force, when I am applying prime mover torque, then only it is rotating.
Yes, sir.
Then only rotating, then only friction will come. To
Yes,
overcome
yes.
that friction only my prime mover torque is working. Therefore,
Yes.
can I say TPM is equal to B into omega?
Yes, sir.
Yes. But is now rotor is 0, na? Rotor is it 0 speed or not? No, not 0 speed.
No, sir.
When I am applying prime mover torque, then only it is rotating, then only inertia, frictional torque will come. Therefore, TPM is equal to B into omega.
Yes,
When
sir.
it is valid, running condition only it is valid.
Yes, sir.
Now, this torque, that torque is equal to 0. For example, you are saying prime mover torque is equal to frictional torque, it will stop. When it is stop means, when it stop means where is the friction? No friction.
Yes, sir.
No friction means, but what is the duty of this prime mover torque? Still I am applying prime mover torque. Will it stop or it won't stop? It It will rotate only. When rotating,
sir.
only friction will come. That equation varied only under running condition. It is running, then only that equation.
Yes, sir.
Only friction increase. Yeah.
Thank you, sir.
Yeah, very good question. Right. Okay. I will stop here. Right. Because tomorrow again we need to continue. Hello? I'm stopping the session. Bye. Anyone is there? Last one? Any last student? Okay.